All right, perfect. All right, we're good to go, guys. At least I caught it early. So where were we? We were into our fun slide. So the finite element method, round number 2. So as we were saying, we went to linear algebra. We covered a lot of linear algebra topics, and you said, well, why exactly are we doing this? Well, basically, we use them for a lot of solid mechanics proofs, right? We covered the Cauchy stress tensor. We covered the green strain tensor. We covered the small strain tensor. We basically just came out with a lot of proofs. Now, this was nice because at the end of solid mechanics, we were able to get one very specific thing, and that was the exact solution of an Euler-Bernoulli beam. Now, that was kind of the goal of the first assignment, dealing with those exact solutions. And we said, well, you know what? Solving a differential equation kind of sucks. I don't want to solve a differential equation. So then we moved into the topic of approximation methods. And in this topic, we kind of said, all right, I have a beam. It's governed by a following differential equation. I can apply either the Rayleigh-Ritz method or the method of virtual work to obtain an approximate solution. Now, it was really nice because that approximate solution, we actually didn't need to solve a differential equation. So this is great because so far in this course, if we were to wrap it up, we have now learned to solve for exact and approximate displacements of beams and continuums. Now, I don't know why I added this 2 separate things. If I were to have this beam right there, and I were to say, all right, guys, solve for this beam, you guys are thinking, Clayton, no problem. Do you want the exact solution? I can give you the exact solution. And I say, well, you know what, guys, I want the approximate solution. And you guys go, oh, well, you want the Rayleigh-Ritz method? Here you go. Oh, you want the method of virtual work? Here you go. You guys are great at this. Now, the problem really becomes is when the beam changes form. So the other beam was supposed to get deleted. Let's see if I can just delete it right now real quick. So what happens if we have this beam right here? What is the problem with this beam? What do you guys think in the chat? Again, this will be nice and interactive today. See what you guys are thinking. It's not uniform. Variable I, exactly. So it has a variable moment of inertia, right? So if you guys were to say, all right, if I wanted to solve this beam, we know that it has a variable moment of inertia because, of course, that cross-section is decreasing. So can we use this equation? If I were to just find I as a function of x1, could I not just substitute that function into this equation and be good to go? What do you guys think? If I could capture I as a function of x1, could I not just substitute it in and say we're good to go? All right, I'm hearing a lot of yeses. The actual answer is no. So this equation that we derived for the Euler-Bernoulli beam here, this equation came from the idea that I was continuous. All right, we only got this that I was constant. We only obtained this equation under that assumption. So if I is not constant, it's actually, the beam does not actually get governed by that equation anymore. So this becomes a problem. All those nice equations, those nice differential equations that we once knew and loved, well, they're no longer valid. So the problem that we have in real life is most of the realistic scenarios that we have, well, they don't follow all those assumptions we made. And if we were to go back and look at Euler-Bernoulli beams, we made a lot of assumptions. First one, linear elastic. Now, most of the time in design under service loads, we do design to be elastic. That's not a big deal. That's not a big problem. However, what do you guys think? Is everything always going to remain nice and elastic? Let's get the chat involved. I'm curious because this is a nice course in the fact that we have more than just civil engineers here. We have mechanical engineers. We have some chemical engineers. So I'm curious, for the mechanical engineers out there, when would something not be elastic anymore? Let's hear an example from mechanical engineering. Because I'm sure that you guys have dealt with non-elastic things before. At least I hope so. Forming steel, yes, exactly, steel. So one of the ones I like to go with, because it's probably the most applicable for civil engineering, is concrete. Now concrete is really good for compression, and it's cheap. That's why we see a lot of concrete structures. However, in tension, concrete sucks. If I were to just put even service loads, everyday loads from regular people on the beam, it's going to crack. And if it starts cracking, that cross-section starts deteriorating. Therefore, the moment of inertia in a concrete beam changes depending on where you're looking at it. Now, another thing about a concrete beam too is that Young's modulus term, that also changes depending on the load. So when we're dealing with real life scenarios, our moments of inertia is almost never constant. Our Young's modulus, also not constant. And just to top it off is they're usually coupled with the loads. Remember, the amount of cracking in a concrete beam, that is going to be based on how much load we put on there. So that I in that equation, it's also going to be coupled with that distributed load Q. So this becomes really, really messy, really, really fast. So the solution to this is the finite element method. The reason why is because we're going to take our problem that is very complex if we were to look at it as just one single problem, and we're going to discretize it into a bunch of smaller problems. But you're saying, Clayton, well, what exactly do you mean by that? Well, let's look at our beam. If I were to look at this varying cross-section, I can see that from x1 is equal to 0 all the way until x1 is equal to L, there's a big variation. However, what happens if I just look at that little chunk right there? Of course, the cross-section is going to change over that little distance. But is it going to change that much? Well, not really. So therefore, in that little section right there, that equation that we derived, it holds true. So this is the idea of the finite element method. We're going to take something that's complex, and we're going to break it into smaller problems that are easy to solve. All right, I hope that makes sense to you guys. So the first thing that we're going to do to show you guys this finite element method, this lecture in general is just more of a nice introduction to the finite element method. Next lecture is where we start talking about the actual beefy stuff. This lecture, we're going to discuss bar and truss elements. So before we begin our actual finite element journey, we're going to begin with bar and truss elements because they are the most simplistic. Again, these elements, they just deform laterally. That's it. There's going to be no shear. There's going to be no moment, nothing like that. It's as simple as, can it expand or is it going to contract? Nice and simple. But even though it is nice and simple, the methods that we're going to use to determine these stiffnesses, as you guys are going to see, it's going to apply to everything. So the exact same methodology that we're going to apply here to these bar elements, you guys can apply it to beam elements. You guys can apply it to solid elements. You guys can apply it to axis symmetric elements, anything you guys want. So right now, today, we're just trying to capture the methodology of the finite element method. And then in the next lecture, we're going to talk about the more complex elements, such as solid elements. All right, so let's look at our beam right here. Let's say that we have a truss element. Now remember, this truss can only deform laterally. So we're not looking at any vertical deformation, anything like that, just purely horizontal. Now, what we're going to do is we're going to say, all right, what I'm going to do is I'm going to take this truss and I'm actually going to discretize it. Remember from the previous slide, we're going to take a big problem and separate it or discretize it into a bunch of smaller problems. How do we do this? Well, we define a series of things called nodes, and these nodes are connected by things called elements. Now, you guys are all graduate students, so I'm assuming that this isn't the first time you guys heard the idea of nodes and elements. You guys are very smart. You guys are saying, Clayton, I know what you're talking about. At least I hope so. So if we look here, these circles that we have, these are called nodes. And these are where we're actually going to calculate all of our displacements. All right, so instead of calculating displacements for the entirety of the beam, like we did in our exact solution or in our approximation method, we're actually only going to calculate the displacements at these particular nodes. Now with those displacements at the nodes, we can apply them throughout the rest of the beam through these things called elements. So each one of these nodes is connected by something called an element. And these elements are actually going to be interpolations. So if I know the displacement at two of the nodes, well, I can figure out the displacement between the two nodes based on the element. And that's what we're going to be discussing today, is this bar or truss element. Now, I got a question for you guys really quick. How many of you guys have taken Civi 660 with Dr. Yong Lee? Does that scare you guys when I say that? What do you guys... Let me know. Let's see. No? Yes? Yes? All right, perfect, perfect. So I see some yeses, I see some nos. And don't worry, we're not going to require anything from that course. But I just want to tell the people that did take it, that idea of the direct stiffness method that you guys learned in that class, that is actually a finite element method. It's the most simplistic finite element method, but it's a finite element method. So everything that you learned in that class, you guys are actually going to see again today. So what we're going to do is we're going to say, all right, well, I know that my whole structure is composed of now these nodes and these elements. What about if we look at just a single element. So if we take a single one of these bar elements, again, we have two nodes, there's an element between them, we have a distributed load P, and at each end of these, or at each one of these nodes, we have a force F. So what I'm going to do is I'm actually going to define something that's going to be important called the degree of freedom. So what happens is these degree of freedoms correspond to each one of the node displacements. So in this particular case, if we were to look at this bar element, we can see that we have one node and we have two nodes. And each one of these nodes, because we're just dealing with a bar element, they can only displace laterally. So for this particular bar element, we would say it has 2 degrees of freedom. One is the node on the left moving laterally, and one is the node on the right moving laterally. And this idea of degree of freedom is actually going to be very important later on once we start coding our program, as you guys are going to see. Now, the whole goal that we're going to have here in the finite element method in general is we want to try and calculate those nodal displacements U1 and U2. Because again, I said that if I have the displacement at each one of those nodes, well, then I can use the element to interpolate between them. So if I have those two displacements, I basically have all the displacements. So that's going to be the goal here. How are we going to do that? Well, we're going to use the Galerkin method. So I actually got a couple of questions, which is great. You guys are paying attention about the Galerkin method, saying that you needed some clarification. Well, I kind of left you guys hanging on purpose last lecture on the Galerkin method, because as you guys are going to see in the finite element method here, the Galerkin method, very important. You guys are going to see it a lot. Now, all these element formulations we're going to do is based on the Galerkin method. You guys may be saying, well, Clayton, I don't like the Galerkin method. I want the virtual work method. Well, you guys can actually use the virtual work method. It'll give you the same answer. Some of you guys may be saying, Clayton, I prefer the Rayleigh-Ritz method. Well, you guys can use the Rayleigh-Ritz method too. It'll give you the exact same answer. So all those approximation methods that we learned, they're actually useful. We can apply them to any one of these element formulations. My particular one, Galerkin method, the reason why it's the most popular. If you guys were to go to a random textbook of finite elements and say, you know what, I want to figure out the formulation of this element, chances are they're using the Galerkin method. And the reason why is because when we look at things like the Rayleigh-Ritz method, it was heavily dependent on that idea of potential energy. Now, a little bit of a sad spoiler alert here. That idea of potential energy, it's only really valid for elastic situations. So when we're dealing with linear elasticity, perfect. It makes it nice and easy. We have our potential energy function. But if we deal with something that kind of delves into plasticity, where we have things like cracking in the concrete or something like that, well, that potential energy function is no longer valid. So this is why we go with the Galerkin method, is because it's general and it can be applied to basically any case. It doesn't really matter what you do. So what we're going to do is we're going to use this Galerkin method to derive two things. There's going to be two things that we want to get out of today. One is the stiffness matrix for these bar elements, and two is the nodal forces vector for these bar elements. Now again, I said that everything is going to be calculated at those nodes, right? So those nodes are going to be very important. However, what happens if we have a distributed load? We know that those distributed loads act between the nodes. So what we actually need to do is we need to take that distributed load and convert it to two equivalent loads located at the nodes. And that's called our nodal force vector. So again, those are the two things we're after today. So we start with the bar. We know that we have a very nice differential equation that governs the behavior of a bar. It's EA multiplied by the second derivative of our displacement function is equal to negative P, where P there is, that's our distributed load. We say, all right, well, we know with the Galerkin method, we want to take our differential equation and we want to set it equal to 0, and we call that the residual. So what I'm going to do is I'm simply going to move P over to the other side, and again, I'm going to call this the residual. Because if the equation is exact, well, this will equal 0. If it's not exact, it will not equal 0. So we call this the residual. Now remember, for the Galerkin method, we want the summation of the weighted residual to be 0 over the domain. Now that just sounds like a bunch of crappy math talk. What this actually means is we want to take the integral over the domain of r multiplied by ni dx is equal to 0. Now, typically we say r multiplied by our weight function wi. But it's very important to know that for this Galerkin method here, our weight function wi is actually equal to our shape function ni. So that's why we have that ni in there. Now, as you guys are going to see, another little spoiler alert, that ni right there, that shape function, that's going to be very, very important moving forward. That's going to be kind of the key to these elements. but we're going to get there in due time, don't worry. So what I'm going to do is I'm going to say, hold on a second. I remember what r is. It's just right above there. So all I did was I took r and I substituted it into this equation here. And I'm going to say, you know what? I don't like this little plus p. I'm simply going to move that plus p to the other side. So all I did was I took our equation from the Galerkin method, I substituted our residual into it, and I created a nice expression. Now we're going to do what everybody loves, integration by parts. So what I'm going to do is I'm going to take that left side there and I'm going to say, you know what? I'm going to do integration by parts. I'm feeling a little risky. Why not? Let's do integration by parts and see what happens. So if we do integration by parts, we get two terms. We get EA multiplied by du over dx multiplied by ni, and this has to be evaluated at x1 is equal to L and x1 is equal to 0. And then I minus the integral over the length of the beam of EA multiplied by du over dx multiplied by dni over dx. So you say, all right, well, that's not too bad. And then if I remember above, well, all this must be equal to negative integral over the length of the beam of p times ni times dx1. So this is really the equation that we are going to play with. Now, what we're going to do before that is say, you know what, I have two negative terms. I'm not the biggest fan of negative terms. I'm going to move each one over to the other side to make them positive. From that, I am left with this equation right here. And this is where all the fun begins. So my first question to you guys, and this is one of the questions I got emailed about in the Galerkin method, and it's actually a lot of fun. What is that term right there? If you guys were to look at that term, can you guys see any sort of relationship that interests you at all? EA multiplied by du over dx. Does that look familiar? I hear yes. Yes. Stress? Almost. This is actually a force. It is stress because we take E and then multiply it by du over dx. Now remember that du over dx, that's strain. So if I take our Young's modulus E, multiply it by strain, I get stress. And since I have that area term in there, if I take my stress and then multiply it by area, I get force. So Omid's correct in that this is the axial force. So this right here is actually the concentrated loads at the end of the nodes. Now as we can see here, we have two terms. We have this concentrated loads at the end of the nodes, and then we have an integral after that. So basically what this is saying, if I were to have an element and I have my two nodes, there's basically two loading scenarios. One is I have a concentrated load at each one of these nodes. For instance, if I were to put a point load P at one of those nodes, that'd be captured by that equation right there. The second equation, the integral, that takes into account the distributed load. Now, what we're actually going to do is we're going to do something a little bit bold here. And this is coming from the simplification of the virtual work method. Remember in the virtual work method how our original equation wasn't a function of the external loads, P, M. It was actually a function of shear and moment. And we said, well, the only time that we have a change in shear at a point is when we have a point load. And similarly, the only time we have a change in moment is if we have a concentrated moment. So we took our virtual work equation and we actually simplified it into the external loads instead of trying to deal with shear and moment. Well, we're actually going to do the exact same thing here. Because what will happen is this will calculate a load at one of the nodes going this way, and then once it gets to the other element, it's going to calculate the exact same force going the other way. So what happens is this actually cancels out completely for most of the scenarios where we don't have an actual point load. Now, because of that, we're actually going to account for this separately. So what I'm going to do is I'm actually just going to delete that altogether. And the reason why is because if we're dealing with finite element analysis, as you guys are going to see, one of the biggest things that we have to be aware of is computation time. If I were to keep that term in, it's fine. It won't change anything. The only difference is I'm going to be calculating a load going this way, and once I get to my element over here, I'm going to calculate the same load going that way. They're going to cancel each other out. So basically, if you guys include that term, you guys will get the same answer. It's going to be no problem at all. The only problem that we're going to have is that you guys are just going to be wasting computation time. As you guys will see, if we're looking at the finite element method today, it's very defined. We have a lot of the stuff that we need. A lot of the focus is now shift to, all right, this takes forever to run. How can I try and make this a lot easier to run? And again, we want to try and follow the same suit. We don't want code that takes forever. So we're going to completely neglect this term. So if we do that, then our following equation is this. We have the integral of EA multiplied by du over dx multiplied by dni over dx. And this is going to be equal to the integral over the length of the beam of P multiplied by Ni. Now we say, all right, well, this doesn't look too bad. The only real question that we've been having is, what is Ni? As you guys may remember from the Galerkin method, this is our shape function, and we haven't defined it yet. And as I kind of mentioned, this is going to be very important because this is going to define the geometric order of our elements. So let's get into shape functions. So let's say that I have a bar element here, and I have two nodes. The first one is located at x1 is equal to x1, and the second one is located at x1 is equal to x2. So it's just two random points. Now, what we're going to do is we're going to first examine something that we call a linear element. A linear element. As you guys will see today, we're dealing with two different types of elements. The first one's going to be linear, and the second one's going to be quadratic. So if we're dealing with this, we say, all right, I have an element, I have two nodes, and let's just say I know the displacement at both of these nodes. Let's say that at the first node, the displacement's u1. At the second node, the displacement is u2. Now, in a linear element, it's going to be fairly obvious, but in a linear element, we assume that the displacement between those two nodes is linear. Therefore, we know from our approximation functions that our element displacement is going to be of the form a0 plus a1 times x1. Again, just a linear function between these two nodes. Now what we're going to do is something a little bit crazy. We're going to say, you know what, Clayton? I know that we loved solving for a0 and a1. That's all we did before. In the exact solution, in our approximations, all we did was solve for a0 and a1. But I told you guys, in the finite element method here, we don't care about a0 and a1. What we really want are those nodal displacements. I want u1 and u2. So what I'm going to do is I'm going to take this expression that we have, and I'm now going to try and switch it up to make it in terms of u1 and u2 rather than a0 and a1. How do we do this? Well, it's simple. We have our equation here, and all I'm going to do is I'm going to say, all right, well, if I were to substitute a value of x1 is equal to small x1, well, then I get the nodal displacement u1. Makes sense, right? Just took my equation, substitute a value in. Same thing at the bottom. If I were to substitute x1 is equal to small x2, well, this should give me a displacement u2, right? Hopefully I'm not losing you guys so far. And I say, all right, well, now I have two equations with two unknowns. Again, my unknowns that I want to solve for are a0 and a1. And if I were to solve for them, I can actually get a0 and a1 now in terms of x1 and x2, those random points, as well as the displacement u1 and u2, as well as L. So L is just the length of this element. I'll add that in there to the notes on E-class so you guys don't forget. So again, if we were to take a step back and look at this, small x1, small x2, again, those are just the coordinates of the nodes. Those are something that we know. So those are no problem. L, that's the length of the node. Or sorry, that's the length of the element. So if I know x2 and x1, well, I can figure out the length. It's pretty easy. So the only real unknowns that we now have are u1 and u2, which is what we wanted. We now have our equation in terms of u1 and u2 rather than a0 and a1. So what I can do is I can take our equation down below, and I'm just simply going to substitute a0 and a1 into our original linear equation. From there, I'm just going to play with it a little bit. I'm going to modify it so that instead of having it as x to the 0 and then x1 to the power of 1, I'm going to modify it so that I have u1 and u2 as my major things. The reason why is because now this function right here, it follows the trial functions that we talked about in the Galerkin method, where u is equal to some constant, in this case it's going to be u1, multiplied by some shape function phi1. And then we go, all right, well then we add some constant u2 plus some shape function phi2. Makes sense, right? So again, one of the things I also want to emphasize, because we're going to be seeing this later, is that u1 and u2, those are nodal displacements, as I mentioned. Those are just constant values. Because again, it's the displacement at a point. It's not a displacement over a range, it's just the displacement at some points. So those are going to be our constant values, which we typically before had as a0, a1, a2, a3, etc. And then in between them, we multiply them by our shape function. Now usually our shape functions were x1, x1 squared, x1 cubed, etc. Well, now they take on the form of this, where n1 is equal to x2 minus x1 divided by L, And n2 is equal to x1 minus small x1 divided by L. So those are just the coefficients in front of u1 and u2. And these right here, these are called our shape functions. And you guys will be saying, all right, Clayton, well, what exactly do these shape functions look like? Well, if I were to plot the shape functions on there, I get n1, u1 is actually equal to this right here. Doesn't look too bad, right? It's just a nice linear equation that goes from our node 2 all the way until u1. And then similarly, if I were to plot the second shape function, n2, I would get this function right here. So if you guys were to look at this and say, hold on a second, if I were to superimpose these, if I were to take n1 and n2 and superimpose them, I get our actual linear displacement, that blue line right there. So this is where it's going to become very, very special. Now, when we look at n2 here, I want to show you guys some specific properties of these shape functions that you guys should know. So this is n2 times u2. But if I were to look at n2 by itself, we notice that n2 has a value of 0 at the first node. And you guys will see this. So if I have n3, it will always have a value of 0 at nodes 1 and 2. If I were to have n4, it will always have a value of 0 at nodes 1, 2, and 3. That's kind of the thing. And from this property, we can conclude something else. n2 will always have a value of 1 at its specific node. So if I was to look at node 2, n2 will have a value of 1. If I were to look at n1, or node 1, n1 will have a value of 1. These are kind of the special things of the shape functions, as you guys will see. But now we can say, all right, well, I now know these shape functions. Remember my equation there, the real unknown I had was ni. Well, now I have ni. It's just n1 and n2. So what I can do is I can say, all right, well, I can figure out my stiffness matrix now. How do we do this? Well, we're simply going to play around with our expression now that we know what those shape functions are. So as you guys remember, we left off with this right here. This was our expression. And we're going to say, all right, well, let's look at this term right here. The derivative of our approximation u with respect to x1. Well, we know that this is actually just going to be equal to u1 times n1 plus u2 times n2. We covered this in the previous slide. Our approximation function is equal to this. And another thing we can say, well, u1 and u2, as I mentioned, those are just displacements at a point. Those are constant. They're not exactly changing. Therefore, if I want to take the derivative du with respect to dx1, it's going to be equal to the following. Because again, u1 and u2, those are just constants. They're not functions of anything. So when we take the derivative, they just remain constants. However, n1 and n2 are two shape functions. Those were a function of x. So therefore, we do take the derivative of dn1 with respect to x1, and then dn2 with respect to x1. Now, what we can do is we can actually make this a little bit, I was going to say prettier, because I personally enjoy it like this, but you guys are thinking, Clayton just made it look gross. We can express this in a vector form, where du over dx1 is equal to dn1 dx1, and then dn2 dx1, multiplied by the vector u1 u2. All right? Hopefully I'm not losing you guys so far. And what we're going to do is we're going to take this expression for du over dx1, and we're going to throw it back into our final expression right here. And this is beautiful because this is actually the one that we end up with for linear elements. We have three things in this expression. The first one right here, this is actually going to be our stiffness matrix. This equation right here, if implemented correctly, this gives you a matrix. And this is actually going to be considered the stiffness matrix of our system, for our element here. The second thing that we have on the other side is our nodal forces vector. So this right here, if I wanted to figure out the nodal forces due to a distributed load, I have my equation right there. And in between those two, we can see that we have a vector u1 times u2. So if we were to look at this, we can say, all right, well, we actually have a linear system here. We have a matrix K multiplied by a displacement vector is going to give me a force vector. And that's the whole goal here. Remember, we want those displacements. Our nodal forces, those are from external loads. We know what those are. And now that we have that stiffness matrix, the thing that relates the two, we're good to go. We can solve for those nodes. Now, I got a question for you guys right now. This equation, the way it is right now, is it one equation? Or is it two equations? Or is it three equations? What do you guys think? This equation right here that I just presented, how many equations is it really? 1, 2, 3, 4? 1. I hear 1. I hear 2. I hear 2. A lot of 2s. It is indeed 2 equations. Now, this is where I'm so proud of you guys. And the reason why is because we have ni right here. All right, we have that ni. So what this means is that we do this equation once for n1, and then we do this exact same equation a second time for n2. And we're going to talk about that. So let's actually examine this stiffness matrix if EA is constant. So what I'm going to do is I'm going to take that formula I just had, and I'm going to say, well, you know what? The only real thing I need to figure out in this formula are those partial derivatives. Well, I know what n1 and n2 are. n1 is simply small x2 minus x1 divided by L. And n2 is x1 minus small x1 divided by L. Therefore, it's easy to say, all right, well, I can take the partial derivatives of these. The first one, well, that's just going to be negative 1 over L. Again, because that small x2, that's a constant. L's a constant, we just have x1 there. And the same thing for the bottom. We only have one x1. Therefore, the derivative of n2 with respect to x1 is simply just going to be 1 over L. Nice and easy. So even though this equation looks like complete crap, this is one of the things you guys will see in the finite element method. We have a lot of equations that look like some big brain next level stuff, like stuff that you find out of Wikipedia. However, it's actually usually pretty simple. Because now that we have these, we can actually substitute them into our equation. But as you guys mentioned, we actually have 2 equations. The first one here is when we substitute n1 for that part over there. So if we substitute n1 in there, well, then we have that negative 1 over L. What this leads us to is this. We have EA divided by L, and then we have the vector 1, negative 1. We can do the same thing for equation 2. So again, the only difference between equation 1 and equation 2 is we're just using a different partial derivative in there. So in the first one, we took dn1 with respect to x1. In our second equation, we're doing dn2 with respect to x1. And from here, we get EA divided by L, and then the vector negative 1, 1. So the stiffness matrix for a linear bar or truss element is simply going to be EA divided by L multiplied by the matrix 1, negative 1, negative 1, and 1. So for those of you guys who took 660 with Yong Li, you brave, brave souls, does that look familiar to you guys? Let me know. Does that look familiar? Yes, yes. So now you guys know exactly where it came from. So this is the stiffness matrix for a linear bar or truss element. Now, one of the things you guys will see in your finite element careers is we typically have 2 options. We have linear elements, and then we have quadratic elements. And this is going to be something that you guys are going to have to try and debate over. This is where engineering judgment comes into play, whether to use linear elements or quadratic elements. So we just covered linear elements. Let's go into quadratic elements. So if we were to go back to our exact same bar here, we say, all right, I know that I have 2 nodal displacements, u1 and u2. But what I'm going to do in this element right here is I'm actually going to introduce a 3rd node. Now this 3rd node, it's going to be at the midspan of our element. So this is where those of you in 660 might start saying, Clayton, I hate you now. Because 660 was nice and easy. Every time we had an element, we only had nodes at the ends of the element. However, if we wanted to, we can place nodes inside of our element. So even though this has 3 nodes, 1, 2, 3, it's actually still just one element. And this is going to make things a little bit more complicated once we try and code it. So what happens is in a quadratic element, as you guys may imagine, our approximation function in that element, well, it's now quadratic, where our approximation is a0 plus a1x1 plus a2 times x1 squared. And we're going to do the exact same process that we did before. Remember, we look at this equation, we say, well, a0, a1, a2, that kind of sucks. I would rather have it in terms of u1, u2, and u3. So what we're going to do is we're going to try and change this approximation to make it in terms of u1, u2, and u3. How do we do that? Well, same procedure as before. We know that u at small x1 must be equal to u1. We know that u at small x2 must be equal to u2. And finally, u at small x3, oh, a little bit of a typo, this is small x3, that is going to be equal to u3. Now what happens when you guys solve this equation, it gets a little bit messy. You guys don't want to know what happens. It gets a little bit messy. It's not very nice. But what happens is we get 3 shape functions in the end. Again, we just use The exact same procedure as before. So if we looked at our linear elements, we had 2 shape functions. But now in our quadratic elements, we have 3 shape functions. Now, as you guys can, actually, I'll ask you guys, if we use quadratic elements, do you guys think that this will increase or decrease the accuracy of the approximation? What do you guys think? Will this make it more accurate or less accurate using these quadratic elements? More accurate, more accurate. Yes, lots of more accurate. Perfect, you guys are correct. More accurate. What's the problem with using quadratic elements? Greater computational time. Exactly. So if we look at our process here, I couldn't show you guys all the steps because it would take me 3 slides. Now, every time that I have to do one of these processes in a slideshow, that's a process that the computer is going to have to do. So what happens is the higher order we get in our approximations, the more computational time it's going to take, and it gets to be very, very messy. So this is why when you guys actually go into your finite element programs, ABAQUS for example, you guys are typically given 2 options: linear elements or quadratic elements. Now, you guys are equipped to figure out what the difference is between them, but you guys will never see cubic elements. The reason why? It just gets too messy. Everything that you guys need can be done with a linear or a quadratic element. And this is why you guys don't see cubic. It gets just too gross, if we're being honest. All right. So from here, we're going to look at these shape functions. So we have n1, u1, we have n3, u3, and then we have a parabolic shape function n2, u2. So just like before. So we're going to move on to the next slide, and we're going to say, well, now that we know these shape functions, let's play around with our equations, see what happens. So again, the equation that we had before we started dabbling into these shape functions was this: integral over the length of the beam of EA multiplied by du dx multiplied by dni dx. And this is equal to the integral over the length of the beam of P multiplied by Ni. So remember that, just like before, our approximation is still a linear combination of those nodal displacements. The only difference now, instead of u1 times n1 plus u2 times n2, we have that additional term there. We have plus u3 times n3. But just like before, our nodal displacements are constant. I don't know why I have the shape function highlighted. It should be just u3 highlighted. Again, just one of those rookie mistakes that I've been conducting today. So from here, we can conclude that our derivative is simply going to be u1 multiplied by the derivative of dn1 with respect to x1 plus u2 times the derivative of n2 with respect to x1 plus u3 times the derivative of n3 with respect to x1. So our final expression becomes this. And if you guys look at this, this is basically the exact same expression we had before. The only difference is we now have a dn3 and we now have a u3. So this right here, exact same as before. This will be our stiffness matrix. We multiply this by our displacement vector. And on the other side, we have our nodal forces vector. Now, question for you guys, how many equations is this one? Remember before it was 2 equations. How many equations will this one give us? All right, someone messaged 3. Any other takers? 3? 3? Oh, you guys are absolutely correct. This will give us 3 equations. All right, so what we're going to do is we're going to say, all right, well, just like before, let's examine the case where our stiffness matrix is constant, or EA is constant, and let's say that x1 is equal to 0 and x3 is equal to L. So basically our element starts at 0 and it has a length of L. Take this gorgeous thing right here. I say, well, I need to take all those partial derivatives. Well, dn1 with respect to x1, it gets a little bit crazy. It's now 4x1 minus 3L divided by L squared. Remember, it just used to be negative 1 over L. Nice and easy. Now it gets a little bit crazy. Same with this one, a little bit more crazy, and then finally the third one. So from here, we can take all these and we can create our 3 equations. So we have the first one here. Again, that vector in the middle there, that will always stay the same. The only thing that's going to be changing is that dni with respect to x1 at the very end there. So in the first equation, it's blue. In the second equation, it is purple. And in the third equation, it is green. So n1, n2, and n3 respectively. So from here, we can get the stiffness matrix for a quadratic bar element as follows. So you guys are saying, well, hold on, this is a little bit more complex. Yes, it's more complex. But again, you get that increased accuracy. So this is where it becomes up to you guys as engineers to figure out, okay, what should I use? Quadratic elements or linear elements? Now, another thing that you guys will see too is this. What happens if I take one quadratic element, so it has 3 nodes, or if I compare it to 2 linear elements, it also has 3 nodes? That's one of the things that we're going to have to consider. So it becomes kind of funny in that you get different paths. I can either have a lot of linear elements or I can have less quadratic elements. You got to kind of pick your poison, if you will. Try and find out which one is the best. So now what I'm going to do is I'm going to do the quickest review of Civi 660 you guys have ever seen, and that is something called the global stiffness matrix. So everything that we've just done until this point was we found the stiffness matrix of one of those elements. But if we remember from the beginning slide, our structure isn't just one element. It's a collection of elements. So what we're going to do is we're going to take the stiffnesses of each one of those pieces and we're going to add them together to create one giant stiffness that represents the entire structure. So these stiffnesses of the elements that we've previously just now defined, we call those the local stiffness matrix. So if I say a local stiffness matrix, it's basically the stiffness matrix of one of those elements, not the structure. What we're going to do is we're going to take all those little local stiffness matrices and we're going to add them together to represent the entire structure. Now this stiffness matrix that we get at the end that represents the entire structure, this is called our global stiffness matrix. All right, our global stiffness matrix. So you guys now know the difference between the two. And now the question becomes, how can I take these element stiffness matrices or the local stiffness matrices and create that global stiffness matrix? Well, it's actually pretty simple. Our global stiffness matrix K is just going to be the summation of all of our elemental stiffness matrices. And you're saying, well, Clayton, that seems a little bit too easy. Well, it does. It's very deceiving. This is the formula, but it gets a little bit more complex than that. And the reason why is because we have to consider those degrees of freedom that we talked about before. Now, I can't use words to describe this. I guarantee the more I try and use words to describe this, the more confused you guys will get. So the best way for me to show you guys this will be an example. So let's say that we had our complete structure as 2 linear elements. So right here I have 2 elements. My first element goes from node 1 to 2, and my second element goes from node 2 to 3. All right, so not too bad. We know our local stiffness matrices. We've already covered these. We said, well, for our linear elements, we know that our my local stiffness matrix is EA divided by L multiplied by the matrix 1, -1, -1, and 1. That's nice and easy. Now the key here to finding this global stiffness matrices is adding what rows of this matrix and what columns of these matrix correspond to what degrees of freedom. So remember that each one of these nodes has a degree of freedom. Node 1 there has a degree of freedom U1. Node 2 has a degree of freedom U2, and node 3 has a degree of freedom U3. So our structure as a whole has 3 degrees of freedom. 1 for node 1, 1 for node 2, and 1 for node 3. However, in these local stiffness matrices, if we were to consider one element, it only has 2 degrees of freedom. So what we're going to do is we're going to relate the degrees of freedom of our elements to the degrees of freedom of our structure. So if we were to look at this first element here, it goes from node 1 to 2. Therefore, it's associated with degrees of freedom U1 and U2. Makes sense. So what I'm going to do is I'm just going to index my matrices as 1 and 2. Nice and easy. Same thing over on the other side. Our second stiffness matrix now, or our second element, it goes from nodes 2 to 3. So therefore, this matrix is actually associated with degree of freedom U2 and degree of freedom U3. So I'm going to index that on here, where I have 2 and 3. So the thing here is now we can say, all right, well, these degrees of freedom, or DOFs, correspond to the index of the global stiffness matrix. All right, so if I were to calculate our global stiffness matrix, all I'm going to do is I'm going to take our matrix, our first one, and say, well, these correspond to degrees of freedom 1 and 2. So I'm going to substitute them in degrees of freedom 1 and 2. I move on to the second element in green there. I say, well, these correspond to degrees of freedom 2 and 3. So I put them there in our matrix 2 and 3. So this, if we look here, the degrees of freedom are actually the indexes of our stiffness matrix. So from here, our global stiffness matrix for this entire structure is equal to EA divided by L, of 1, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, and 1. Now I got a question for you guys in the chat. Those of you guys who love Yong Li will know the answer to this. As we can see, those far corners of that matrix, they're 0. Will they always be 0? What do you guys think? I hear a no. Yes? Ooh, some competition. The answer is no. It is symmetric, yes. So they will always be the same. That's correct. But they may not specifically be 0. They may be some number. And the reason why is because when we're dealing with these bar elements here, it's very easy to see a sequence where we go from node 1 to 2 to 3 to 4, all in a nice linear line. If that's the case and everything's in a nice linear line, then yes, we're going to get a very easy to determine matrix. But remember that another word for these bar elements is truss elements. Have you guys seen truss elements? Or not truss elements, trusses? You got members going all over the place. So at one of those nodes there, instead of just having one element on each side, we might have 6 elements going to the same node. But that's some Civi 660 crap. I'm not going to deal with that in this course. I'm just trying to show you guys the methodology. So as long as you guys know the methodology of what we're trying to do to assemble this global stiffness matrix, we're good to go. So once we have the global stiffness matrix, or actually at the end, we can solve the system. But there is a little bit of a trick to it. And this comes with the Galerkin method. Remember in the Galerkin method, if I told you guys, I said, if you don't implement those boundary conditions, you guys get infinite solutions. And someone messaged me and they said, how, Clayton? And I said, that's a great question. I never talked about that. How did we get infinite solutions? Well, let's clarify that right now. So let's look at this problem right here. Let's say that we want to solve the following problem where we have a beam fixed at one end and it has just a load P at the other end. And what we're going to do is we're going to solve this using 2 linear elements. So I have 3 nodes, and in between each one of those nodes is an element, right? Nice and simple so far. Well, from the previous slide, because it was basically this scenario, we know that our global stiffness matrix is simply EA divided by L of 1, negative 1, 0, negative 1, 2, negative 1, etc. So the first thing that we need to solve these problems is going to be that global stiffness matrix. We know that our displacement vector is going to be U1, U2, U3. Again, it's just all the degrees of freedom. And finally, our nodal force vector is a combination of 2 things. The first one is our nodal forces, which we call Fn. As we can see here, we have Fn. Now, these are the nodal forces due to a distributed load. That's that integral of P times Ni that I was telling you guys about. Now, in this particular case, we have no distributed load, so it's going to be equal to 0. Now, remember that term that we canceled out. We said that, well, you guys can include it, but basically you're just taking something and then subtracting it, then you're adding and subtracting, you get nothing, and we account for that separately. Well, this right here is that accounted for it separately part. So this right here is going to be all the concentrated loads, externally concentrated loads that we have at our nodes. So if we were to look at our node 3 at the end here, we know that we have a concentrated load of P. So we simply just have P here. At our middle node, we don't have any concentrated load at all. So it's going to be 0. Now my question is, why do I have R1 there? What do you guys think? What is R1? I don't have a concentrated load that I see, do I? Why do I have R1? Reaction. Oh, you guys are too smart. Too smart. It's the reaction, exactly. So since this end is fixed, we know that even though we don't see it, there's a reaction force there. Otherwise, if there was no reaction force and I were to take the bar and pull it, well, it's just going to get pulled away. But since we have that reaction force, it creates that reaction, therefore we have R1. Now my question to you guys is, well, it's obvious in this picture, but in general, do we know what that reaction force is? In general, of course. I know you guys are looking at this and going, well, it's obvious, Clayton, but in general, do we know what that reaction force is? Yes, it's equal to P. But in general, we don't know what that reaction force is. If I were to give you, like, this is a simple scenario. If I were to give you an indeterminate truss structure right now, indeterminate, and I would just say, what are the reactions? You guys won't know what the reactions are. So in general, this is unknown. Of course, in this scenario, again, yes, very easy to tell what it is, but in general, we don't know the reactions of things. So our reactions are actually an unknown. Now remember that we said that we had a linear system. We had our stiffness multiplied by our displacement is equal to our forces. Nice and simple. Well, the problem is if we substitute something like this, we have unknowns on both sides. Remember, we don't know what those displacements are. That's what we're trying to solve for. But we don't know what the reaction is. Now the question became, in the Galerkin method, I said, if we don't incorporate those boundary conditions, we get infinite solutions. The reason why is because if you don't implement those boundary conditions, this is what you're trying to solve. Something with unknowns on both sides. Not very, very easy. So what do we know that can actually help us solve this? What do you guys think? Oh, Oswald, right on the money. We know that U1 is equal to 0. We know that that node at the very end there on the left, it's fixed. Therefore, the displacement there, U1, must be equal to 0. Now what we do is when we have restriction in one of our nodal displacements or degrees of freedom that is fixed, what we can do is we can cancel out the columns and the rows corresponding to that. So since we know that U1 is fixed, I can take the first row and the first column of my matrix and just say bye-bye. Cancel it out, nice and easy. Now, of course, there's better terms than just cancel it out and saying bye-bye, but that's just what I like to say, so hopefully you guys don't mind too much. Now, what's nice is because we are now left with just this right here, where we have EA divided by L, and then we have the matrix 2, -1, -1, and 1, times U2, U3 is equal to 0 and P. Well, we know what P is. Remember, that's an externally applied load. That's not a reaction that we can't figure out. We know what P is. We know everything on the stiffness side. Therefore, we can actually solve for U2 and U3. Nice and easy, right? Now, the secret here, and this goes back more into Civi 660 than it does in this course, is once I know U2 and U3, I can actually substitute them back into this equation up here. So let me just get rid of the mess here. Now that I know U2 as well as U3 and U1, because U1 is just equal to 0, I know everything on this side over here. Therefore, if I wanted to, I can solve for that reaction force. Nice and easy, right? Right? Perfect. So this is what we do. We solve for those nodal forces. Now, even though I don't have a slide talking about it, you guys already know that if we have those nodal forces, we know the displacements of the elements, because our elements are just simply displacement functions. For instance, if I were to go all the way back, let's go back, where'd be a good slide? Probably this one right here. Oh. So remember that we had our displacement of our element for a linear element as simply a function of U1 and U2 right here. So since I know now what U1 and U2 is, I have now my displacement approximated over the elements. Another thing that I can do is I say, well, I know my approximation function. As we saw before when we dealt with beams, I had my approximation function. That means I can also find my shear function. I can also find my bending moment function. So for this particular case, we don't deal with shear and bending moments, but what can I use this for? What can I use this for? What do you guys think? If I were, what is one of the things I'm interested when it comes to bars or trusses? Axial force, exactly. I can figure out the axial force in all of my bars now that I have my displacement function. So that's the theory, guys. How are you guys feeling? You guys just learned the finite element method in what? 1 hour. How was it? Now, of course, this is 2D. This is simple one-dimensional. Next week we get into two-dimensional, so don't worry. It's going to get even more fun. But this just right here, how are you guys feeling? Is this too crazy? Not too bad? What do you guys think? Curious to know your thoughts. Looks all right so far? Perfect. Because I'm going to let you guys in on a little secret, just between us, so don't tell anyone. This right here, this is the most complex it's going to get. When we deal with 2D things, it's going to get a little bit more complex, of course. But the nice thing is the methodology stays the same. It's the exact same thing. The only difference that we're going to have in 2D, as well as 3D, as well as anything else, we're just going to have different shape functions, different approximations. So if you guys just have different shape functions, well, you guys just know, just substitute them in. We're good to go. Now, a nice thing too about this course, and I didn't want to tell you guys this yet, but here's the other secret. If you guys notice under assignments, I only have assignments 1, 2, 3 posted. So you might be wondering, well, Clayton, what does assignment 4, 5, 6 look like? It's going to be a lot of abacus. What do you guys think of that? Do you guys think that's a good thing that it's all abacus, or do you guys prefer the way it is right now with the theory? What do you guys think? You guys excited that it switches more to an abacus focus rather than a theory focus, or you guys prefer the theory? You guys are happy it switches to abacus? Yes. Because everything that we just did in there, we're going to code. And that's going to be the focus of this last part of the lecture. So if we were to look at assignment 3 right here, what I want to do is I want you guys to code. And I know that I'm making you some of you guys cringe. Like, code? Oh, I don't like coding. And that's what I find. It's the funniest thing with graduate students. I find that they either love coding, I love coding, or they hate coding. Like, absolutely hate coding. This is the last assignment where you guys are going to need to really code something. There's another assignment where you guys need to code a little bit more, but it's actually pretty simple. This is the only assignment where I'm going to actually get you guys to code the finite element method, but we're going to do it together. All right, so that's the goal. I don't want to stress you guys out. I know some of you guys hate coding, so we're going to take a break here soon. We're going to come back and we are going to code the assignment together. Nice little group activity. But real quick, I just want to show you guys what the assignment is. So the first part is just finding our nodal force vectors. I'm going to let you guys do that. You guys have the nice equation for the nodal force vectors. It's simple. It's just the integral of P, which you guys can figure out what P is, multiplied by Ni. Well, those are our shape functions. We know our shape functions for our linear elements, and we know our shape functions for our quadratic element. So nice and easy. Question 2, that's where it gets a little bit more fun, and this is why we are going to do it together. So the first question says it wants the exact solution and stress distribution of the beam. What do you guys think of that? Pretty easy? Yeah. We know that this beam has a very simple differential equation. There is no discontinuities. No problem. The second part, this is when it gets fun. It says it wants the displacements of the nodes and stresses within the elements if this bar is modeled using 4 linear elements. 4 linear elements. So this is where that iteration comes in that a lot of you guys will learn to hate, is we cover the stiffness matrix for one element. How can we make a computer program that will just go through all of our elements and then take all the stiffnesses from each one of those elements and then create one giant stiffness matrix? The second part here, the displacements of the nodes if the bar was modeled using 2 quadratic elements. So we're basically going to code the entire process that we just discussed. So it's going to be a lot of fun. I got this tablet here, which I'm going to boot up to try and if I need to clarify something using drawings, because when we code something, it's usually good to draw something out to figure out what's going on. But before we do that, we should probably take a break. So why don't we take a 10-minute break? We'll come back at around 9:16, 9:17, and we'll begin the fun then. All right, guys. I'll see you guys at 9:16. All right, guys, welcome back. So, kind of a quick question for you guys. Can you guys see the Mathematica screen? Once I plugged in this monitor over here, oh my gosh, my video is displayed over on the drawing tablet. Hold on. Where's the mouse? Alrighty. Perfect. All right, sorry guys, I didn't see the chat. So can you guys see the Mathematica screen? Once I plugged in this, everything kind of went crazy. All my monitors switched. Perfect. So you guys can see the Mathematica screen. So what we're going to do is we are going to solve our thing right here. Right? Nice and easy. Or is it nice and easy? Well, let's find out together, okay? So the first thing that we always do when we're dealing with Mathematica is we just want to define what our parameters are. So I'm just going to come down and I'm going to go parameters. Nice and simple. And I don't know where the I don't know where the document went. Alrighty. Yes, this is being recorded on this screen now. That's why I had to switch everything over, is because the recording transferred over to this screen over here. So in this particular case, we have a couple basic parameters. We have EA, and we set it equal to 1. That was kind of in the thing. We have L. we'll set that equal to 1. Well, actually, now I'm not too sure what they are. Oh, here it is. So let's see. We have L is equal to 2. L is equal to 2. EA. Oh, we have to actually figure out EA. So let's just put this to the side just while we input our parameters. I don't know how to get rid of this. This is new to me. All right, so we know what E is. E is our Young's modulus, and it says that we are given 10,000 MPa. So what do you guys want to do? Do you guys want to do MPa, KPa? What are you guys feeling? Again, we're given right here that it is 10,000 MPa. You guys want to do MPa? Perfect. We'll go MPa. You guys know what I like. So if this is an MPa, what should our moment of inertia be in? We're given that our moment of inertia is 0.1 meters squared. Should we keep it in meters? Millimeters to the 4th. All right, so we know it's 0.1 meters, so I'm just going to go 1 divided by 10. As you guys know, we keep it in fractions so that everything else ends up being a fraction at the end. But why do we need to multiply this by? 1 divided by 1,000 to the 4th. What do you guys think of that? Does that look good? I got an okay? Any other okays? There's a lot of confusion. All right, so there's too much confusion. Here's what I'm going to do. I'm going to simply solve for EA, and this is a bar element, so it's cross-sectional area. That's why. You guys are smart. But I'm just going to keep it general, and you guys can play with this all you want. So I'm going to post this code after class, and you guys can figure out your own parameters. All right, so P, that's our distributed load. We have that is equal to 4 times x1. So I'm just going to go 1 times x1. It'll make sure that you guys aren't just copying all the code all the time. So those are going to be our parameters. Now what I'm going to do is I'm actually going to add in one more parameter just to make it really fun. And that is the number of elements that we want. So in our first case, it says that it wants us to model it using 4 linear elements. So what I'm going to do is I'm going to say my number of elements is equal to 4. And we're going to code this so that we can change the number of elements and it'll do everything else for us, which is really, really nice. So now that we have all the parameters, we can actually get into the fun stuff. So before we get into the actual fun stuff, I'm going to do some preliminary calculations, something that'll help us out along the way. So preliminary calculations. These are going to be things that we use quite a bit and just makes our lives a little bit easier. So the first one that we'll use quite a bit is the number of nodes. So this is where all that interactive fun chat comes into, you guys. If I have 4 linear elements, how many nodes do I have? N plus 1, 5. Yep, you guys are exactly correct. So if I were to go number of elements plus 1, would that make you guys happy? It's all about keeping you guys happy. As long as you guys are happy, I'm happy. Quiet? All right, I'll take it that you guys are happy. So another one of the things that I want to do is I want to try and keep track of the locations of each one of these nodes. All right, I'm going to keep track of the locations of each one of these nodes. And what I want to do is I want to create a vector. And the vector is going to be the location of node 1, the location of node 2, etc., etc., etc. So in this particular case, if we have a length L, and we know that we have 4 nodes, well, it's going to be 0, L divided by 4, L divided by 2, 3L, etc., etc. So again, I just want to create a vector that has the location or the coordinate point of each one of these nodes. So the first thing I'm going to do is I'm going to define what the element length is, okay? I want the length of one of those elements because, again, that appears a lot. So I'm going to go EL. I'm just going to call this my element length. What will this be equal to? If I know the length of the beam, L, and I know the number of elements, what would be the length of my elements? All right, Sabrina, you're right on. So this is going to be L divided by the number of elements. So if I were to do this right now, it simply says 1/4, and this makes sense. If I'm using 4 elements and our beam is of length L, then each one of the nodes is going to be at a distance L/4 from each other, or basically the quarter points. So again, what I want to do is I want to try and create a vector that has all the locations of those nodes. So this is where it gets a little bit tricky. I'm going to call this vector L. This is just going to be the location of each one of these nodes. Now to do this, I'm going to use the table function. The table function. You guys really haven't seen this much. You guys may have seen it a little bit in Civi 664 if you guys are doing displacement gradients, but probably not here. So what I'm going to do is I'm going to give it to you guys, and I'll show you guys exactly what this table function does. What this does, it creates a table. That's why it's called a table function. So it's going to take in two inputs. So we're going to separate each one of those inputs with a comma. The first one is going to be what is kind of the function that defines each entry of our table. And then the second one is going to be kind of like a for loop. What is going to be the range? So each one of the entries is simply going to be I times our element length. And what we're going to do is we are going to go from I is equal to 0 all the way to the number of elements. Now again, I'm just giving you guys this because I want to show you guys what exactly this is. And I got to move my... I have my video screen way over on the second monitor, so it looks like I'm breaking my neck always trying to look at you guys. So if I were to run this right here, I get this vector. I get 0, 1/4, 1/2, 3/4, and 1. Now this makes sense, right? Because all I did was I took this function right here, and then for each entry, I just varied I from 0 all the way until the number of elements, so 4. So in the first entry, 0, 0 times the element length, well, that gives me 0. And then it moves on to the next one. So 1 times the element length, that's 1/4. Goes to 2, 2 times the element length gives me 1/2, and it goes all the way to the number of elements, which is 4. So we get 4 times the element length, which is simply just 1. So did I lose anybody thus far? You guys see what I did here? Just created a nice vector having all the locations of all the nodes. Are you guys happy? Oh, yes. Yes, thank you so much. You are completely correct. That would have confused me a lot later on. Perfect. So other than that, you guys are pretty happy? Now what's nice about this is because, again, we're making everything parametric. So let's say that I wanted 6 elements. I run that. I now have my vector for all the locations of all 7 nodes. Nice and easy, right? So we're going to go back to 4, just for fun. So another thing that I like to do in these preliminary calculations is I like to define our stiffness matrix, our global stiffness matrix, as well as our global nodal forces vector. And the reason why is because every time we create the stiffness matrix of an element, we add it to the global matrix. Now, if we don't define what that global matrix is, well, then we're adding something to nothing. So it makes no sense. So what we like to do is we like to start by creating a global stiffness matrix of just zeros. All right, so it's just going to be straight up zeros. And what we do is every time that we create a stiffness matrix of an element, we start inputting those entries into our global stiffness matrix. Now, it may not make sense right now, but it'll make sense a little bit later. So what I'm going to do is I'm going to say my global stiffness matrix. I'm going to call it KG. I'm also going to create it with the table command. Now, this is going to be a matrix. So the first one up here, we got a vector. And the reason why is because we only had one input. We went from I is equal to 0 to the number of elements. What I can do is I can add a second input, which says that J goes from 0 to something, which will start creating a matrix. So what I'm going to do is I'm going to say that this is going to be just a bunch of zeros, and I want to go from I is equal to 1 to the number of nodes, comma, J goes from 1 to the number of nodes. So if I were to run that, I get this. Now, it doesn't look like much, but if I were to put this in matrix form, like this, as we can see, we got this. Now, my question for you guys is, I just did number of nodes for fun. Is that correct? Is our global stiffness matrix going to be 5 by 5? Or did I make a mistake? What do you guys think? Should it be 5 by 5, or am I just, have I lost my mind? Elements instead? Oswald says okay. So this is why I brought out the drawing tablet. So I'm going to try switching my screen, and you guys let me know if this works. So I'm going to go over to screen 3. Do you guys now see a black screen? Hopefully. Yes? Perfect, perfect. So let's see how well this works. So I just got this thing. This is the reason why the videos have been a little bit slow lately. It's because all the videos that I'm doing by hand, I'm going to try using this thing, but I've never used it before. So what I'm going to do, all right, let's see if I can figure out how to use this thing. Let's go with this. So if we have our beam, can you guys see what I'm drawing? Hopefully. Yes, perfect, perfect. So we have our beam. Now we know that we are doing 4 elements, so therefore we have 5 nodes. So if I were to go, we got node number 1, 2, 3, 4, 5. 5 nodes. Now each one of these nodes has 1 degree of freedom, right? We already talked about that. So right here, we'd have U1. Right here, we'd have U2. We have U3. U4, and we have U5. So now that you guys see it like this, do you guys agree that our stiffness matrix should be 5 by 5, or did I make a mistake? Remember that each one of those rows in our global stiffness matrix corresponds to a degree of freedom. Are you guys satisfied with 5 by 5 now, knowing that we have 5 degrees of freedom? Correct? Perfect, perfect. So that's exactly why we have it, because we have 5 degrees of freedom. So the number of degrees of freedom in these very specific cases is related to the number of nodes that we have. Now again, if we were to get into a crazy complex truss structure where we have multiple elements going to the same node, well, things get a little bit more complicated. But again, that's some Yang-Lee crap. We're not getting into that in this course. Now I got to find out where my mouse went to. All right, perfect. So we define that. Now, what I'm going to do is, again, I'm going to define our force vector. So what I'm going to call is, I'm just going to call it Fn, nodal forces vector. We're going to use the table command yet again. And again, I just want to create it as zeros, because every time I do an element iteration, I'm going to slowly add it in. So we're going to have 0, and yes. Oh, yes, thank you for pointing that out. So yeah, I'll probably do that a lot. Make sure you guys remind me. Should be good to go now. All right, I'll delete this all. So now what I'm going to do is we said, all right, we have our global stiffness matrix as just a matrix of zeros. We can create our global force vector as just a vector of 0. So again, using the table command, our entry is going to be 0. And what are we going to do this over? We're going to go from I is equal to 0 to what? What is going to be the size of our force vector? 5, 6, 7, 5? Yes, you are completely correct. So we're going to go all the way from there to the number of nodes. So this creates a vector. We can see that we have 5 unknowns. So these are all the preliminary calculations that we want to do. All right, nice and simple so far. I'm hoping so. Now we're going to get into the fun stuff. And this is where we're going to start looping through things. And this is where students start hating things. They don't like loops. So what we're going to do is we're going to derive the stiffness matrix for a single element, and then we're going to add the loop in later. If we can derive the element, or derive the stiffness matrix for a single element, we're usually pretty good to go, and adding the loop in after, it's pretty simple. So the first thing that we need to do is we need to say, all right, what is going to be our displacement approximation? So this is what it's going to be in terms of A naught. So if I were to go displacement is equal to, now in terms of A naught, and if I'm doing linear elements, am I going to go A naught plus A1x, or am I going to go A naught plus A1x plus A2x squared? What will be my displacement approximation for these linear elements? Sabrina says A naught plus A1 times X1. You are completely correct. Nice job. So A naught plus A1 times X1. And it's that simple. Now we said that when we have this displacement approximation, we don't like it the way that it is. We want it in terms of our element displacements, our nodal displacements at our element. We don't want it in terms of A naught and A1. So what we're going to do is we're actually going to change these coefficients to be in terms of our nodal displacements. So I'm just going to call this switch to switch to nodal displacements. I can't spell today, guys. I'm sorry. So what we're going to do is we are going to simply substitute our displacement function at each one. So what I'm going to do is I'm actually going to pull up the PowerPoint, because this will probably make it easier to show you guys what exactly that we did. So where is that slide? Right here. So again, if I wanted these in terms of our nodal displacements, what I did was I substituted the value of our left node and our right node to create two equations. And we said that, well, at our left node, that's going to be equal to the displacement u1. And then at our right node, this is going to be equal to the displacement u2. So from here, I created two equations. I can solve for our two unknowns. So all I'm going to do is I'm going to take that displacement approximation, which we defined already, and I'm going to substitute the value at the left-hand side of the node and the value at the right-hand side of the node, its coordinates. So I'm going to do is I'm going to say, all right, well, equation 1, this is going to be my displacement approximation, specifically when x1 approaches the left-hand side of the node. Now, this is where things get a little bit tricky here, because remember that our nodal coordinates change. What I'm going to do is I'm going to switch to the screen. Go back here. So you guys can probably see now. Lost the pencil. So right here at this node, this is x is equal to 0. This one is x is equal to L over 4. X is equal to L over 2, etc., etc. So every time I do one of these nodes, I have to keep updating. Because again, I'm substituting this value, and then I'm substituting this value for this element right in the center there. But when I move on to the next element over here, well, then I'm substituting this value, and then I'm substituting this value. Does that make sense to you guys? That I have to keep updating this. So what I'm going to do is I'm going to utilize that very nice nodal vector that we have right here. So I'm actually going to unsuppress this. I'll delete this really quick so I can keep it out. So we're going to use this nice... Oh, yes, thank you. It's so much easier in a video. I can just edit it out all the time. All right, so we have our nodal forces vector here, and these are the coordinates. So for our first element, which goes between 0 and 1 over 4, I'm going to input these two coordinates. And then for our next one, I'm going to go from here all the way to here, and then from here all the way to here, etc., etc. So I'm going to say my equation 1 is going to be equal to our displacement, specifically when x1 approaches L of 1. Oops, not I. Right, so I'm calling on this one right here. Then I know that my second equation for this first element, so equation 2, is going to be our displacement when x1 approaches L of 2. So if I were to actually run these really quick, I get this. I get a naught, and then I get a naught plus a1 over 4. So what, again, I'm trying to do is I'm trying to solve for a naught in terms of u1 and u2. So I'm going to create, I'm going to use the solve command. So I'm going to go solve. And what I'm going to do is I'm going to say my equation 1, which is the displacement at x1 is equal to 0. Well, that, of course, is going to be equal to our displacement, which I'm going to call x1. I'm going to say equation 2. Well, this is going to be equal to our nodal displacement, which I'm just going to call x2. Remember, x1 and x2, those are what we're trying to solve for. I'm not calling them u1 and u2 because we're going to use that a little bit later and it'll start confusing the variables. So I'm just going to call it x1 and x2, but these are just the nodal displacements. And these are what we're trying to switch a naught and a1 into. So what we're doing is we're solving this equation for a naught and a1. And if I do that, I get a naught is equal to, this is basically u1, and a1 is equal to negative 4 u1 minus u2. So what I can do is I can come down here, and I'm just going to store a1 and a2 as a naught and a2, specifically when solution of 1, and I have just a1 and a2 stored. Nice and simple. So what I can do now is I can figure out what my shape functions are, because my shape functions are actually just going to be the coefficients. So if I were to actually run really quick my displacement function, I don't have a naught and a1 anymore. I have u1 minus 4x1 times u1 minus u2. That's all I'm doing. Nice and easy. So remember that our shape functions are actually just going to be the coefficients in front of all of these. So what I'm going to do is I'm going to go shape functions. And our shape function n1, it is going to be the coefficient of our displacement function in front of u1, which I called x1 in this case. So this is our first shape function, 1 minus 4 times x1. Our second one is going to be the exact same thing, so I can just copy and paste it. But instead of n1, we now have n2, and instead of u1, we are going with u2. So from here, I'm going to create our shape function vector, ni, and this is just going to be n1, n2. And I don't know where I didn't, right here. So have I lost you guys yet? All I did was determine the shape functions. Probably lost you guys a little bit. I know it gets confusing. This is why I wanted to do it together. Let's go back to the PowerPoint just to see exactly what I coded in. So the first thing that I did, yes. So that's what we're trying to really emphasize. What we just did right here, this was only for one element. Remember that when we set x1, this goes into x1 is equal to 0, and this one is x1 is equal to 1/4. So this goes from node 1 to node 2. So this is just for one element right now. We are going to loop it a little bit later to show you guys how to go through all of the elements. Now, I want to just go back and show you guys what we did. So all I did was I took our location 1, substituted into our value, and I set it equal to u1. I did the same thing over here, set it equal to u2, and then I was able to solve for my a coefficients. From there, I was able to take those a coefficients and I threw them back into our displacement function, and then I rearranged our displacement function to get this form. So when I did coefficient there, what the coefficient did was basically give me this term in front of u1, and then when I did the second coefficient, it gave me this term in front of u2. And then what I said is this coefficient in front of u1, this is equal to our shape function n1, and this coefficient in front of u2, this is equal to our shape function n2. So I hope that makes sense. What do you guys think? So far, so good? I don't want to lose you guys, at least not this early. Maybe later on. Hopefully. If you guys have any questions, please let me know. Let's try to do this together. Nice and fun. All right, no one wants to say how they're doing? All right, that's fine. That's fine. Oops, not delete. I wanted to go enter. All right, so now that we have our shape functions, one of the things that we always did with those shape functions, if we go back to the PowerPoint, is we kept taking the derivatives of them. You see how we have the derivative of n1 with respect to x1, and we have the derivative of n2 with respect to x1, and we have just the derivative of ni with respect to x1. So one of the things that we should definitely do is take the derivative, because it just appears so much all the time. So I'm just going to go derivative of the shape function. And this is actually very simple, because remember, in Mathematica, we have that d command. So what I'm going to first do is I'm going to define what variable is. So we'll go d of ni. So this is going to be my derivative of my shape functions. And this is simply calculated using the derivative function in Mathematica. Now this takes in two inputs. The first one is, what is the function you want to take the derivative of? Well, we want to take the derivative of ni. And then the second one is, what do you want to take the derivative with respect to? Well, we know we want to take it with respect to x1. So I got a question for you guys. This ni right here, it's a vector. We defined it as a vector above. Will this derivative function work? Or will Mathematica just say, Clayton, you're an idiot. You threw in a vector when you should have threw in a function. What do you guys think? You think it's good? Or do you think that we just shot ourselves in the foot? Let's try. I love it. That's exactly what I do. If I think something's going to work, I just try. So if I were to go shift enter, we're good to go. It's able to take the derivative. And what it does is it takes the derivative of n1, puts that as our first part, and then takes the derivative of n2. It puts it at our second part. So now that we said that we had ni, if we go back to our thing, we said this is perfect, because now I know everything in our stiffness matrix formula. I can actually figure out what that stiffness matrix is. So what I'm going to do is I'm going to come down, I'm going to go stiffness matrix. Now, question for you guys. Is this going to be the global stiffness matrix or the local stiffness matrix? Local? Local? Yo, you guys are on your game. Yes, this is indeed the local stiffness matrix because this is the stiffness matrix of the element itself. So if we go back into PowerPoint, which I just always lose it, we see that it's going to be the integral over the length of the beam of EA multiplied by that derivative vector multiplied by the derivative of NI. So what I'm going to do is I'm going to come down here. I'm going to say our stiffness matrix K, and I'll call it KE for just the stiffness matrix of the element. We know that it's the integral, so we're going to use the integrate function, which takes in two things. The first one here, that's going to be our function, and the second one is our domain. Well, our domain's nice and easy. We're integrating all the way from 0 all the way until L. Now what we're integrating, well, that's going to be EA, as we just saw, multiplied by our derivative vector, so that's going to be d and I, and then multiplied by d and I, specifically at I. So this is the thing, is we actually have two equations. We have to remember that. So if I wanted to, I can do this. I can create the stiffness matrix kind of 1, where I have d and I 1, copy, I'll just paste it here, and I can create the second part here, where I have d and I 2. Because remember, we had those two equations. So if I were to run this, I can create this. But how can I make this just nice and simple in terms of one matrice? Do you guys think you guys know of any functions in Mathematica where I can do both of these calculations just basically at once? Was there anything that we did earlier where we can just iterate through I as many times as we want? Yes, the table function. You guys are on your game. So remember that here we have this, but what I'll do, actually, I'll just keep it the same for now, but I'll just go KE, and instead of going DNI 1 and then a separate one of DNI 2, we can just keep this as DNI I, and what we're going to do is we're just going to use the table function on this. So I'm going to go table of this, comma, we're going I from 1 to 2, because we have two equations. So if I were to run that, I have it as one nice simple matrix. Nice and easy, right? So I can delete these, and I now have my stiffness matrix for my element. So if I were to go KE matrix form, this is what I get. Nice and easy. So that's for the stiffness matrix of the element. Now another thing that we have to get before we can start adding things to the global scale, oops, I wanted to get rid of this, and I'll get rid of this too. Otherwise it starts confusing everybody. Another thing that we have to calculate before we start adding things from the local level to the global level is their nodal forces vector. So I'm just going to go here, nodal forces vector. All right, nodal forces vector. Saying, Clayton, what exactly is the nodal forces vector? Well, if we go back to our PowerPoint, if it pops up, and we're to go here, our nodal forces vector is simply this, the integral over the length of the beam of P multiplied by d and I. Oh, good question. That's a great question. I've been on this game. He's right. I'm wrong. When we're dealing with the first element, we just don't go from 0 all the way to L. We go over the domain of the element. So this would technically be L of 1, which is 0, to L of 2, which is L over 4. Thank you for pointing that out. We would have had some mistakes and we would have had to debug. This is why group things are so nice. It's because you guys always find my mistakes and it makes it easier for me to not look like an idiot so much. Or maybe it makes me look like an idiot a bit more, but oh well. That's okay. All right, so you guys feeling pretty confident? Thank you for pointing that out. That is a great catch. So the nodal forces vector, we're going to be doing basically the same thing. So where is my PowerPoint? So really quick, nodal forces vector, right here. One equation or two equations, if I were to just consider this part at the end here. What do you guys think? I hear 2. Any other takers on 2? You guys feeling 2 today? Ah, you guys are shy now. Well, Mahmoud, you're completely correct. It is indeed 2. So since we're dealing with two equations, just like we had for the stiffness matrix, we're going to use the table function. So I'm going to go table. And again, I'm going to input what I want to iterate over, and our second part will be how many times. So we're going to go from I is equal to 1 all the way till 2. So we can account for both of those equations. Now, what exactly are we iterating over? Well, we said that the nodal forces vector is the integral. So I'm going to go the integrate function. And my domain, just like before, is going to go from x1 is equal to L1 all the way until L2. And what we're doing is we're taking our distributed load P and we're multiplying this by Ni of I. Again, all we did was we took our exact formula that we have right here and we just threw it into Mathematica. We really had no manipulation. It was just making it nice and simple. So if I were to run this right here, I get this right here. So what exactly is this value? What do you guys think? What is this value right here? If I were to ask you guys on the exam, what is that value right there? The force at node 1. Mahmoud, correct again. On your game today. So what happens is, since this element goes from node 1 to node 2, and we have that distributed load across the element, what we did with this function is we took that distributed load, which goes all the way across the element, and we converted it into two nodal forces. So again, took that whole distributed load, and then we changed it into a load at node 1, and then a load at node 2. So that distributed load that went over this beam, it's the same as 1 over 96 point load at node 1 and 1 over 48 point load over at node 2. All right, so that's it. Nice job. That's a good one. So now that we calculated both the local stiffness and the local nodal forces vector, we can start adding them to our global forces and global stiffness vector. So what I'm going to do is I'm just going to go add element stiffness to, not top, to global stiffness. So how do you guys suppose we tackle this? Now here's one of the things. If you guys took 660, we know that we can create some really nice code that'll go over everything in a nice little loop. But we're not in 660, and I'm not Young Lee. So what we're going to do is we're going to do the cheap way. We're just going to go element by element and just make it look simple. All right? Makes sense? Or at least hopefully. So if I was looking for the global of 1, 1, the first entry in our global scale. Actually, this is where the screen will come in handy. So what I'm going to do is I'm going to share back. And we are going to play around a bit. Where's that pencil? All right, so what we're going to do is we're going to say we are looking at these nodes right here. Let's see if I can switch the color, actually. That might make it a little bit better. So we're dealing with node 1, and we're dealing with node 2. Sound good? I got to turn around to see you guys. All right, and we know that our global stiffness matrix is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, etc., etc. So I actually don't need to draw the rest, but I might as well, just so you guys can see. So this is what we defined as our global stiffness matrix right now. And we said for this particular element, so this first element right here, we said that we had a matrix of, I'm just pulling it up, so you guys actually don't need to see. We said that our matrix was 4, -4, -4, and 4. So this is what our Mathematica code gave us for that local stiffness matrix right here. So this is, again, of our elements, and this is our global right here. So what we're going to do is we are going to take these degrees of freedom, and we are going to translate them to the global scale. So I'm going to switch colors again. So we know that this corresponds to 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. Now, if I look at this element right here, we know it goes from 1 to 2. So therefore, this is the same as 1, 2, 1, 2. Does that make sense to you guys? What do you guys think in the chat? Pretty good? I'm probably not even sharing the right screen. So what we're going to do is we're going to say this right here This is located at 1, 1. We can see that from our industry. Index. Oh my God, I can't say indice. There we go. So what we're going to do is we're going to take this value at 1, 1, and we are going to put it at our global stiffness at 1, 1 right here. So what we're going to do, I'll switch to erasers. We're going to say that this, instead of 0 now, this is equal to 4. And we're going to do the same thing over there. So I'm going to switch to back to the pen. I'll do a different color. This one right here, this is at 1, 2. So I'm going to bring this over to entry 1, 2. So instead of this being equal to 0, we now know that this is equal to -4. Make sense to you guys? At least hoping so. Sorry, just getting pop-ups on the window. And we can do the same thing for the other two. So I'm going to erase these two because it's very obvious to see that these two bottom ones right here, which I just, that is not a very nice color. Looks like poop. All right, we got -4 and we have 4. And that's all we're really basically doing. So the nice thing here is this right here never changes. We always have entry 1 and 2, but in our global one, we're going to change it. So I'm going to come over here. I'm just going to share back the screen. Share. Perfect. All right, so K11, well, we said that this is going to be equal to K element. Is that how I define it? Yes. This is going to be the same as 1, 1. Makes sense to you guys, right? Same as 1, 1. Now, if I were to go down to the second one, 1, 2, well, this is going to be equal to the element, 1, 2. And what I can do is I can just repeat the same process for the rest. So I'm going to go 2, 1. Well, this is equal to KE 2, 1. And finally, we have KG at 2, 2 is equal to KE 2, 2. So we actually created a big problem. And it's not very obvious yet. And we have a couple problems that we're actually going to have to deal with. So if I were to run KG right now, our global stiffness matrix, we have the following, where all the entries that we wanted to are exactly where we want them to be. So far, we're so good. But once we start looping this, that's where all the problems start happening. But we'll get into that once we start looping. So far right now, we're good for now. So what we're going to do is we're going to also add our nodal forces to the global forces. So just like before, I'm just simply going to go, oops, sorry. I got an itchy hand here, guys. I'm just going to go my Fn, oops, not Kn, Fn at 1. Well, this is going to be, how did I define it? Oh, I didn't define it. So we'll go, this is the force of the element up here. So Fn is going to be equal to force of the element at 1. Similarly, Fn at 2 is going to be equal to the force in the element at 2. So if I were to go Fn in matrix form, all it did was it took my two entries and put them into the correct spots. So that's all we did so far right now. What do you guys think? Are you guys happy right now with what we've achieved? If we were doing one element, this would be perfect. We would have everything we need to know. The problem is, of course, we don't have one element. We have, well, how many do we have? We have 4 elements. So what we're going to do is we are going to take all this code that we just wrote. So basically from our displacement approximation to down to here, we are going to loop over this code for every single element that we have. Does that make sense to you guys? We found out everything we need to know for one element, which is great, but we have more than one element. So what we're going to do is we're just going to loop over until we account for every single element. Make sense? Hopefully. I see some good, some yeses. Perfect. So in Mathematica, the for loop, it's very simple, very similar to MATLAB, very similar. It's actually more similar to Python, actually, which is kind of funny. So what we're going to do is we're going to go for. The first input is where are we starting? So let's say that we're going to start from I is equal to 1. Actually, let's go j, just because we use I quite a bit everywhere else. So we're going to start at j is equal to 1, and then we're going to specify our endpoint. So we're going to stop when j is less than or equal to of when. If we're going over our elements, would this next entry be the number of elements or the number of nodes? What do you guys think? I hear nodes. Nodes again? It's actually the number of elements. Because remember, we just obtained a stiffness matrix for our element. If we were to go the number of nodes, you're implying that we go over 5 times. That means we have 5 stiffness matrices, but we only have 4 elements. So we actually go over the number of elements. That makes sense. If we have 4 elements, we need 4 stiffness matrices. If I were to go 5, well then that means I have 5 stiffness matrices, but I only have 4 elements. So this is actually equal to the number of elements. All right. So what we do is we specify first where we start. Well, j is equal to 1. Where do we end? Well, this basically says j is equal to 4, our number of elements. And then what is our incrementation? Well, we're just going to go I++, which means it's going to go from 1 to 2 to 3 to 4, etc. Now, after that, we put a comma in. And then after that, we go all the way down here, and I'm going to end that square bracket. J++. Thank you, guys. Yes. So where did my loop start? J++. Perfect. So all of this from here all the way down, it's going to loop 4 times. 4 times. Now, we basically have all the code that we need. And what I'm going to do is I'm actually just going to tab it over real quick. Oh, not delete it. All right, I don't know how to tab it over. In Python, it's easier. But basically, all we're going to do is we're just going to go through our code again, and we're just going to switch every time we have like a 1 or a 2, we're going to switch it with j, because j will always make sense. So our first one is we took our displacement at x1 is equal to 1, and then x1 is equal to 2. Now, we know that we actually have to keep switching this. So what I'm going to do is I'm going to come up here to our L vector, and I'm just going to unsuppress it. Of course, we got an error because we didn't fix anything yet. So remember that from our first element, we went from 0 to L over 4. Makes sense. Now, for a second element, we are going from 1 over 4 to 1 over 2. Third element, we're going from 1 over 2 to 3 over 4. So basically, I'm going from j and then j plus 1. And then our second element, we go j to j plus 1, etc., etc. So by the time we get to 4, which is our last one, we have this one right here, and then we go to j plus 1, which is this one. Does that make sense to you guys? If I were to come up here, and instead of 1, I were to put j, and if I were to come down here, I go j plus 1. Does that make sense? Hopefully. I can repeat it again. All right, makes sense? Perfect. So after this, we're solving our equation for x1 and x2. Remember that these are just variables. These don't really matter, so we don't actually have to change those. We come down here, we are good to go. So do we have to change anything in our shape functions to account for this loop process? What do you guys think? Do we have to change anything when it comes to our shape functions? All right, we hear a no. No, you guys are correct. So if we're not changing the shape functions, well, then we're obviously not changing the derivatives either, right? Makes sense. So now when we get down to here, though, and we're doing our local stiffness matrix, do we have to change something in here to account the fact that we're looping through it? Yes. Perfect. So what are we changing in our local stiffness matrix? We said that EA is just going to be EA. We said that the derivative of our shape functions isn't going to change, and our shape functions themselves are also not going to change, but you guys are right. We're changing the integration limits. So instead of going from 1 to 2, we are going from j all the way over to j plus 1. Perfect. You guys know exactly what you guys are doing. Perfect. So nodal forces vector, just the same thing? What do you guys think? Just this exact same thing? All I need to do is just change these two. We're good to go. You guys have been good. I'll just say yes. So yes, j. Now we're going over to j plus 1. So those are actually the more or less the easy ones. Okay, those are the easy ones. It's when we get down to here to this matrix that things get a little bit more different. So the question is, do I need to change I is equal from 1 to 2? The answer is no. And the reason why is because all this accounts for is the fact that we have 2 equations. That's it. So every time we do one of our integrals here, where our equations go, every time we go to each element has 2 equations. So that I equals 1 to 2, that just says that we have one equation and then we have a second equation. Does that make sense? Why we don't change I equal 1 to 2? Hopefully it makes sense. All right, I'm just going to assume it makes sense, but if you have questions, again, ask me whatever you like. Again, it's just because we have two equations. Each one of these linear elements will always have two equations. Now, question for you guys. Yes, and that's exactly what I was going to ask. So Amber's on his game. In our quadratic form, down here, we have three equations. So in that case, we would need to change it for our quadratic from I equals 1 to 3, because in this case, we have three equations. So nice job, Amber. You know exactly what is going on. Perfect. So now let's get into the stiffness matrix. So now I got a question for you guys. Every time we calculate the local stiffness matrix of an element, it's always going to be 2 by 2, correct? If I were to come back here to my PowerPoint, and I were to go to my linear element up here, we see that our local stiffness matrix is always going to be just a 2 by 2 matrix, right? For each element, it's just 2 by 2. Does that make sense to you guys? It's always going to be 2 by 2 for each element. Now, since it's always going to be 2 by 2, do these parts over here actually change? KE11, KE12, KE21. Will these ever change? These over here? Sabrina says no. Sabrina, you are absolutely correct. Nice job, guys. Because again, this element stiffness matrix C will always be 2 by 2. Therefore, if we were to put a J in there and our J goes to 4, it's going to call an entry that actually doesn't exist. So what happens is these are the ones that are actually going to change. So just like before, every time that we have a 1, we're going to replace it with a J. Every time we have a 2, that's simply just J plus 1. What do you guys think? Do you think that's good enough? If I would just go J, 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 oh, 2 here, so I'm going to go J plus 1. And then here, oh, 2, so J plus 1. Oh, I got a 1, so I'm just going to have J. And then I'm going to have J plus 1. Oops, lost where my mouse went. J plus 1. Oops, do you think that's good? What do you guys think? Am I just pulling stuff out of my ass? Yes, so this works great for if our beam is just a series, basically a line, really. However, if we have those intermediate joints, this gets more complex. But I'm going to tell you guys a little bit of a secret here, all right? So don't tell anyone. This is between us. I will never give you intermediate joints on the final exam. So for your final exam, I'm more interested in you guys knowing the finite element method, not 660 structural analysis. All right? So yeah, exactly. Structural analysis is terrible. If I wanted structural analysis, then we'd also have to account for the coordinate transformation matrix, which accounts for if the bar was at an angle, stuff like that. Oh, it's gross. Don't worry about that, guys. So for our particular case, this will work just fine. But Ahmed raises a great point, and this is one of the problems that I wanted to talk to you guys about. And we're going to get to that in a second. All I'm going to do really quick is I'm going to come down here, and I'm going to switch these two for J plus 1 as well. Do I change these ones over here? FE1 and FE2? No, you guys are right. Perfect. So what I'm going to do is, seemingly our code works. So what I'm going to do is I'm going to display our stiffness matrix KG. And our code does not work. Why is that? This is the fun part about coding. They're not the same shape. All right, I'll get to that in a second. I don't even know where that is. X1 minus X2, not a variable. Oh, okay, yeah, so I know exactly what's going on. This is another problem too. So you guys, actually, this is something you guys will be very familiar with. So if you guys don't clear any of the variables, when it gets back up to this equation, equation 1's defined, right? Remember, the whole point here was to solve for equation 1. But if we come up back to this point and loop around, and it's already defined, well, then we have a problem because we have something equal to something. We don't have an unknown. So every time that we loop, we actually also need to clear our solving variables. So in this case, we need to clear A0, A1, And what else should we clear? Equation 1, equation 2, and our solve function. Does that work? Perfect, perfect, perfect. So do you guys understand why that happened? It's because we already had variables solved by the time we looped back up. So when we came to the logical stuff, it made no sense at all because we already technically solved it. But we have to solve it again for each element. So that's why we have to clear it each time we go around our loop. So this is what I wanted to show you guys right here. It'll work a couple times, but then it'll start getting messed up a little bit. So this right here, I'm going to get rid of our nodal vector. So what do you guys think? Is this right here the correct global stiffness matrix? Amber already hinted that he disagrees, and I agree with him. What's the problem? It looks pretty. You guys know what the problem is? Internal nodes? No, that's actually not the problem. The problem is actually how we wrote the code. Yeah, we did not add it properly. So what we're going to do is we're going to come over, and I'm going to share the screen over to the other side here. Share. So you guys can see this screen right here. Hopefully. Drawing screen, we're good to go. Back on the drawing screen. All right, I'm going to assume you guys are correct. So we got this for our first matrix. Now, let's say that we were interested now in our second element right here, right? Second element. Now, since all these elements are the same length and the same cross section, this will also be 4, -4, -4, and 4. Again, all the same length, all the same cross section, etc., etc. So if we were to look at the degrees of freedom for this one, and I'll switch to, let's say, light blue, we know that this goes from element 2 all the way until, or sorry, node 2 to node 3. So this is going to be 2, 3, 2, 3. Therefore, if I were to look at this entry right here, that entry right there, we know that this is going to go into 2. So this is going to go right here. But we already have 4 there from our previous stiffness matrix. If we look here, entry 2, 2 appears up here, and I'm just going to try and highlight it because I'm making a mess now, and it appears in here. So when we're dealing with our global stiffness matrix, this entry right here is going to be 4 plus 4, which is actually equal to 8, right? Does that make sense to you guys? I'm hoping so. Hoping so. Yeah, all right, yes, I'm getting the yeses. Perfect. So I'm going to switch back to the screen right here. Share. Oop, wrong screen. And if we look at our stiffness matrix that we got, everything is right except for these entries right here where we have 2 elements acting on the same node. It doesn't account for that addition. And the reason why is because when we defined it right here, we just kept overwriting that variable. So what we actually need to do is this is going to be equal to our global stiffness matrix initially. So I'm going to go kg of j comma j plus whatever addition we do to the element. Does that make sense to you guys? Basically, our stiffness matrix after the element is going to be our initial stiffness matrix plus the stiffness from the element. That's what we're doing here. So I'm just going to copy this right here. Control V. And we're going to have to modify it, of course, so don't worry. We're going to go modify it after. So this one we have j and then j plus 1, so I'm going to add the plus 1 here, add the plus 1 here, plus 1 here, and finally I'm going to add the plus 1 over there. So if I were to run it now, we can account for that addition. So now everything is looking pretty good. How about our nodal forces, though? Fn. If I were to write Fn in matrix form, do we also need to account for that addition that we've been having? What do you guys think? Yes, exactly. So our Fn at j is going to be equal to Fn at j plus the element there. Right here, we're going to go, got some hair on my hand, Fn, oops, not 2 n's, j plus 1 is going to be equal to f of 2. If I were to run that, looking much better. Although I don't know why I'm getting the j plus 1 down here. Oops. Interesting. Plus not equal to? Yes, you guys are completely correct. Plus. What did I do wrong? This should be j plus 1. These are for the nodes. 2, 3, 4. Why am I getting 6? The vector force has 6 elements. Sorry, what? I'm getting confused. I am confusing everybody else too. I equals 1 to 2. This should be for each one of the nodes. And these are all correct. I just don't know why Fn had 6 elements to begin with. Ah, that's what it is. You guys are so smart. Thank you guys. See? Isn't coding fun? This is why some people hate it, but I love it, because once you guys find that mistake, doesn't it feel great to find it? Well, it doesn't feel as great because you guys are finding it for me, but you guys know what I'm saying. So at this point, we have a correct global stiffness matrix. We have a correct force stiffness matrix. We're good to go. We can solve the system. Sound good to you guys? You guys want to solve the system? Let's solve this system. So if I were to go really quick, let's, what should we call it? Displacements. We can solve the system using the linear solve command in Mathematica. Now it's nice and easy. It's going to say if you have a matrix times a vector, which is equal to a vector, all you're going to have to do is input the matrix. Well, we know that that's going to be our global stiffness matrix. And then we have to input our vector. Well, we know that that's going to be our force vector. Oh, we got a problem. What happened? Did we forget a step? What do you guys think? Why is Mathematica telling me that I'm an idiot? Boundary conditions, exactly. Exactly. So what we actually need to do is we need to modify both of our stiffness matrices and our nodal forces vector to account for that boundary condition. So what I'm going to do is I'm going to go boundary condition. And remember that all we're going to do is we're going to drop the rows and the columns of our matrix at the location of that boundary condition. So I'm going to create a second matrix, global matrix, and I'll call it BC. So this is going to be my stiffness matrix after I apply my boundary conditions. And what this is going to be equal to, so I'm just going to go equal to, we're going to use the drop function. So all the drop function is, it's nice and easy. It takes in 3 inputs, or if you have a vector, 2 inputs. So I'm going to go 3 inputs. It's going to say, what is the matrix that you want to modify? Well, we want to modify our global stiffness matrix. It's going to say, all right, what rows do you guys want to drop? So if our boundary conditions at U1, what row do we want to drop? The first row, the second row, the third row? The first? First, you guys are correct, first row. What column do we want to drop? First, you guys are good. So if I were to run this now, it's still trying to solve this equation. Let me just delete that really quick. If I were to run that now, I now have a 4x4, which is what I wanted. I'm going to have to do the exact same thing to our nodal forces vector. So I'm going to go after boundary conditions, and we're going to do the same function. So we're going to drop it. We know that we're dropping things in our forces vector, so I'm just going to go Fn. Now, which row do we want to drop in this one for our forces vector? All right, I'm hearing 1. Are you sure? Are you sure and positive? What do you guys think? Are you guys positive? All right, I got another direct message saying 1. So I'm hearing 1s, but are you guys positive? How sure are you? Let's try. The point is, it is correct 1. What I'm trying to show you guys is be confident in yourselves. You guys are all very, very smart students. There's no need to second guess yourselves. So if I were to run this, I now only have these forces right here, which is perfect. All right, so now after we do that, then we can solve our system. So solve, not our system, solve our system. I'm going to come down here. Again, I'm going to use the linear solve, so I'm going to say that my displacement vector, yes. So our displacement vector after we apply the boundary conditions, this is simply going to be the linear solve of our stiffness matrix, capital K, Kg, after the boundary conditions, and our forces vector after the boundary conditions. So if I were to run that, I get this right here. Now, what are these right here? What are those special values that we were just given? Displacements, but displacements where? Nodal displacements. Exactly, nodal displacements. So this right here, this will be the displacement where? At node what? So a lot is saying 1, but I hear 2 and 2. Remember that at node 1, it was fixed. So what's the displacement at node 1? 0, exactly. So these are the displacements of the non-fixed nodes. So this will be node 2, node 3, node 4, node 5, etc. All right, and that's basically it. So after you guys solve for this, you guys are basically done. You guys can go back into your functions, nice and easy. So what I'm going to do is I'm just going to open up a special code that I've already prepared, and this is the code I'm going to give you guys on E-class. So where is it? Right here. So it's the exact same thing that we just did. There's no modifications. I just added a little something to the end to show you guys some clarifications. Now, the code appeared on the drawing tablet. Hold on, I gotta figure that out. All right, perfect. You guys see it scrolling into screen? So again, this is the exact same thing that we just had. We coded all this together. We went right up to this step right here. So after this, all I said was I took my solution and I just added the boundary condition to it. So instead of having nodes 2 to 5, I just added 0 in front, so I counted from nodes 1 to 2. So if I were to do this, this is just my complete nodal displacements. After that, I just went through my approximations, because again, if I had the nodal displacements at each end of the element, I can find the approximation between the elements. So that's all I did here. And then down here, I just created a piecewise function. Why did I do that? Well, I just want to graph it, really. So that's all I did there. Now, what I did at the very top was I selected 2 nodes. 2 nodes. So I come down here, I have my exact solution, which is the blue line, and then I see that I have my FEA solution, 2 nodes. So I have a node here, I have a node here, and I have a node here. What do you guys think of 2 nodes? Pretty good approximation? In terms of displacement, are you guys pretty happy with 2 nodes? Or sorry, 2 elements? Yeah, no, I agree, it's good. So the thing to keep in mind when we're dealing with these elements, and we're going to discuss this a lot more next week, is some of the requirements of elements. And one of them is called their continuity. So one of the things that we can see is since we picked linear elements, that means that the displacement is linear. What this means is that the strain is going to be constant, and therefore the stress is going to be constant. So even though our displacement function looks not too bad, when we get to the stress function, it looks like complete crap. So this is one of the things that you guys are going to see. So you guys may be saying, well, Clayton, why don't we just, increase the number of nodes, or sorry, number of elements. So let's come up here. How many elements do you guys want? You guys want to try 10? Let's try 10. So we run that. As you guys can see, the more it starts adding the computation time. So as we can see, it gets a little bit better. One of the things that, again, we have to realize is that since we picked linear elements, it's discontinuous all throughout that stress profile. It gets a little bit better, but as you can see, it's pretty gross. Our actual solution looks pretty good. So one of the things I also want to just show you guys really quick is I'm going to go back to 2 nodes so you guys can see this, is that at our nodes, okay, at our nodes, is it the exact same as the exact solution? Yes, it is. Now, will this always be the case? Ooh, gotcha. No, it will not always be the case. The only reason why this is the case is because our exact solution is a polynomial. As we're going to see later on, most of our time our exact solution will not be a polynomial. So what we're going to see is at the nodes, it'll still be very, very close to that exact solution, but exactly the same, probably not. The thing to keep in mind here, and this is all I'm trying to show you guys, is when we're dealing with this FEA, we make sure that our displacements at the nodes are very, very good. So our displacements at the nodes, very, very good compared to the actual solution. It's what happens between the nodes, aka the element, that we start seeing the error. How do we increase that error, or decrease that error, sorry? Well, one of the solutions, as we saw, we can say, well, instead of 2 elements, let's have 10 elements. So if I run it, as we can see, the more elements, the more computation time, but it starts getting better and better. Now, another thing that we can do is we can use quadratic elements. So that's the second part of your guys' assignment, is you're going to take the code that I gave you here, and you're just going to modify it for quadratic elements. And as Amer's saying, it's the shape function for the elements. If we were to do a quadratic, let's go back to 2 elements. If we were to do a quadratic, well, we know that between node 2 and node 3 here, we actually have a quadratic function. So therefore, that quadratic can actually better approximate this curve. Actually, I'll show you guys. So I have the quadratic done, but I got to give you guys something in the assignment, right? So let's see how long this takes to load. Oh, I'm always wondering where the heck it is, but it always appears on the drawing tablet side. So here's for the quadratic element. See, this is 2 nodes. And as we can see, it's almost bang on, 2 elements. It's almost bang on for 2 elements. And if we look at our stress function, it's now linear instead of constant. So it kind of helps. So that's quadratic and linear nodes. Hopefully you guys figured out what to do. Now the nice thing for you guys is that after you guys are done this assignment, no more coding the finite element method. As you guys see, it sucks. It's just iterations, looping over all the elements. It's not fun. We have something called ABAQUS to help do it for us, which is great. So what we're going to do is we're going to take about a 10-minute break. I know that you guys are thinking, Clayton, there's only going to be 25 minutes left to lecture. Or no, 15 minutes left, but that's all I need. So what we're going to do when we come back is I'm just going to show you guys a brief introduction to ABAQUS. All right, so that's all I'm going to do. So I'm going to exit out of this, and we're going to take that 10-minute break, and because if we don't, I'm going to lose my voice. And don't worry, I'm going to post that code on eClass. So before we go real quick, any questions about the assignment? Are you guys confident that you guys can do the assignment now that we went over it together? Hopefully. Hopefully, yeah. Don't worry. That's my special word is hopefully. Did you guys like going over it together, or would you guys prefer if I just cut the lecture early and let you guys go do it by yourselves? Well, yes. So the lecture slides are going to be posted right after this too. I was just modifying them right before the lecture today. My apartment flooded over the week, so it's been a little bit crazy compared to most weeks. So I apologize for that, guys. I'll be better after this. Together is great, perfect. So from now on, when we do examples, we'll do it together to try and make it as nice as possible for everybody. So again, hopefully the assignment will be good. We'll rendezvous at 10:35 just to show you guys a brief introduction into ABAQUS. Nothing crazy, just show you guys what exactly is what. So I'll see you guys at 10:35. All right, guys, welcome back. Let us start the fun of ABAQUS. So as I kind of mentioned a lot in this course, ABAQUS is going to be where it's at. So starting with assignment number 4, every assignment you're going to have, so 4, 5, 6, 7, 8, 9, we're all going to be doing ABAQUS in it. Now, ABAQUS is a finite element program, and it's nice because it basically does everything that we just did by hand and had to code ourselves. It does it all by itself, so it's great. So I take it that you guys have installed Abacus by now. So when you guys open up Abacus, you guys are going to get this black screen. It's basically just checking if there is a license available. So 14 out of 20 still available, pretty good. And you guys are opened up with this main page. Now when you guys first see this page, it's disgusting. Like, there's so much to look at. There's so many different things to do that it could be a bit overwhelming, if I'm being honest. So what I typically do is I just exit out of this first part, and this takes us into our model. So even though it looks like we have a lot of stuff, we basically have no model right now. Now, the nice way that I like to think of Abacus that just makes it a little bit easier is I go up to this module right here, this module. Now, if I scroll down, these are basically going to be all the steps that we're going to need to do once we start modeling things ourselves. So the first one is going to be part. This is where we create the parts that we're going to use in the model. And you're going to say, Clayton, well, what do you mean by parts? Well, it's hard to explain. Let's say, oh, this is the best way. So I study masonry, right? You guys have seen masonry, concrete block, or bricks, anything you guys want. We know that a masonry wall isn't just made of one material. It has masonry bricks, and it has mortar, and inside we have steel, stuff like that. So each part is one of those constituents. So for example, in this part module, I would make my brick, and then I'd make my mortar separate. All right, so this is where I create all the parts. After that, I go into the property module, and this is where I take those parts that I created, and I basically give them some meaning. I give them material properties. After that, I go down into assembly, and this is where I take all of those individual parts. So for instance, my brick, my mortar, etc., and I assemble them into just basically one giant wall. After that, I can go to step, and this is where I start applying my loads on the wall. And then after, I basically just go to job. So I just rushed through that because I thought the best way to actually show you guys would be to do what we just did, basically. So what we're going to do is we're going to take an actually loaded bar, and we're actually going to model it. So what I'm going to do is I'm going to go into my part module, and how to create a part? Well, it's simple. We have two options. One is we go up here. It says create part, or two, we can go down to this parts tab right here. So if I double click this parts tab, it says create part, and it gives me a bunch of options. Now, if I wanted to, if I don't want to do that, I can click this button up here, create part. It actually is the exact same thing. So we're going to be asked a couple questions. The first thing is, what do you want to name this part? Well, we're just going to call it our bar, nothing too special. And then it's going to ask you about the modeling space. So we have 3D, we have 2D, and then we have axis symmetric. And I'll explain what axis symmetric is in future lectures. It's a nice way of modeling cylindrical things nice and easily. But for our bar, we know that we are having it in the 2D plane. Now, what are we going to have it as? Well, it's going to be deformable. Of course, we're measuring displacement. If we keep it as rigid, well, there's no displacement. So there's no sense in putting it as rigid. So it's going to be deformable. And then its base feature, we're going to make it a wire. So shell elements, those are the most typical finite elements you guys will see. Those are the 2D elements that have all the nice colors in them. We're actually going to discuss those next lecture. But since we're dealing with a bar, which is basically just a string that we pull axially, we actually treat it as a wire. And it makes sense because, again, we're just pulling it axially. We're not actually shearing it or anything like that. Now, this approximate size, this last one, this doesn't really matter. What this does is it gives you a drawing space, and this drawing space will be this big. Now, it doesn't matter in the sense that if you were to draw outside of the drawing space, well, nothing's going to happen. It's still going to create the part just fine. So I just leave it as default, and I go continue. So this is what I mean by the drawing space. If I were to zoom out, as we can see, our grid stops at a certain point. This is that 200. It only gives you a grid for that approximate size. But if I wanted to, for instance, if I wanted to draw a circle outside of this grid, well, it's no problem at all. I can do that. So even though it looks like it's something you need to know, it's actually not something you need to know. So for our wire, we're going to define it as simply a wire or a line. So we have a number of options here. So we have circles, we have rectangles, ovals, curves, etc. So once we start modeling more complex 2D shapes, we are going to get into these, especially when we start dealing with solid elements. But for now, we're just dealing with a bar, which is just, again, simply just a nice wire. So what we're going to do is we're going to come right here, and I'm just going to create a line. So I'm going to zoom in a bit, and then down here it actually says I can pick the XY coordinates of each point along this line. So let's say that our line starts at 0, 0, so right there. And let's say that it has a length of just simply L. or actually let's make L equal to 1. So this ends at 1, 0. So because our approximate size is 200, 1 is very small, but basically I just made this line right here. So what I can do is I can go done, and then we are given our bar element. But now if we actually consider this, this is nothing. This is basically just a line, nothing else. It has no material properties. It has no mesh size or shape functions, anything like that. It's just straight AutoCAD at this point. So what we're going to do is we're going to take our bar, which again is nothing at this point, and we're going to say, well, we know what the material properties are. So I'm going to go from our part down to my properties tab. Because I created the part, I have all the geometry, I can now assign it material properties. So there's a couple things that we need to do. The first one is going to be the most obvious, create a material. So we can do that again by clicking this button, or I can double click this material tab on the side. Now, what do you want to call the material? Well, we can call it anything we want. Let's say that our bar is made of steel. All right, so I just put steel in, and then down here we can specify the mechanical properties. So the general ones, these are things like density, stuff like that. That's nothing that we really need to consider unless we're doing dynamic analysis. When we're talking about stress strain curves, those are actually the mechanical properties of the material. So as we can see down here, there's a lot of things that you guys may already know. For example, plasticity. I hope by this point you guys all know what, elasticity. I hope you guys all know what elasticity is. Plasticity, again, a lot of you guys will know what plasticity is, but we're going to cover that a little bit later. And let's just say that our bar is linear elastic. So I come down to the elasticity section, and I'm just going to define it as elastic. Those of you who took solid mechanics, you guys may be more familiar with hyperelastic, stuff like that. A little bit more complicated, but not too bad. So we're just going to keep it elastic. Now notice the one of the things it says is isotropic. This is one of the things that we covered in solid mechanics. So this is why we do all that review. Because once you guys get to this point, you guys will be very well familiar with all the terminology that's going to be used. So we're going to keep it isotropic, and it asks for two things. The first is the Young's modulus, and the second one is the Poisson's ratio. So if we're doing steel, we'll have the Young's modulus as 200,000 MPa. Now the same thing that we did in Mathematica applies here. Whatever units that you guys have, it's fine. You can use whatever. Just make sure that it's consistent. So if I'm doing MPa, well, then I'm going to be putting newtons and millimeters. The second thing is the Poisson's ratio. So I can specify a Poisson's ratio, let's say 0.3. Why not? Because it's steel. That's one of the nice things about the finite element method is we start accounting for those things that we neglected before. So we're actually accounting for Poisson's ratio in this case. So I say, okay, I have my material defined. So if I drop down the material tab, I have a material, but ABAQUS doesn't know what this material is related to. Again, this beam right here, or this bar, it's simply just a shape. It has no material at this point. So what we're actually going to need to do is we're going to have to take this material that we created, and then we have to apply it to this bar element. Well, we have to do that through the section command. So just below the material thing is we have this section right here, or down here section. So I'm going to click that right here, and it says, all right, what do you want to create? Well, we're creating a section for our bar. So I'm just going to call it bar. Now, typically we do solid sections. As you guys are going to see, solid elements are going to be something we use all the time. But the bar element is a very special case, and it's actually found down here in the beam section. So under the beam section, we have two types, beam, which you guys are familiar with, and truss. Remember that the bar element is also called a truss element. So we're actually going to go truss element right here. Go continue, and it's going to ask for two things. One, what is the material property of this truss element? Well, we said that it's equal to steel. If I were to have multiple materials defined, for instance, if I had masonry and I had masonry, grout, mortar, horizontal reinforcement, etc., well, my list would be huge here, and I just simply drop it down and pick what I want. Since I only have the one material defined, it automatically goes to that one material. Now, the part down here, it says, what is the cross-sectional area? Now, of course, when we remember our calculations for these truss elements, they had that EA term. That area term, well, we're actually accounting for it in ABAQUS right here. So I can set my cross-sectional area as whatever I want. Let's say that it's equal to just 10,000, nothing too special. So from there, I created a section. So I'm saying, all right, well, I have a bar, and it is of steel material. Now what I'm going to do is I'm going to take this section and apply it to the shape that we just created. So I'm going to go down here, and it says assign section. So what I'm going to do is I'm going to select what we just created, go done, and it's going to say, all right, what is the section associated with this? Well, the only section we created is bar. So I'm going to go continue. And if you guys did it correctly, it will now turn green. All right, so that's how we define one of these parts and assign it properties. From there, we can go down into our assembly module. And this right here, this is our actual model. So this is where we take all of the parts, combine them together, and then analyze it. Well, how do we bring in those parts in? We have a button right here that says create instance, or basically bring in the part. If I were to drop down the assembly module, I have an instances part right here too. So I can double click this. It says, all right, which part do you want to bring in? Well, as we can see, I've only created one single part, so my only option is to bring in the bar. So I can go OK, and now I have my bar in my model space. But again, the thing about this space is I can bring in as many things as I want. If I wanted to, I can bring in a second bar, no problem. So now I have 2 bars, but of course I don't want 2 bars. I just want to analyze the single bar. So I'm going to delete that right there, and I'm going to analyze this single bar. So once we bring it into the model space, we can start assigning loads and boundary conditions. So what I'm going to do is I'm going to go to the next section, which is the step tab. Now the step tab is actually hard to explain, but it's very, very simple. This defines the sequence of events. Now normally when we just load something, we just load it, watch it fail, and then it's done. So there's only really one event, which is the loading. But let's take a cyclic loading, where I take something, I squish it, then I pull it, then I squish it, and then I pull it. Well, each one of those motions is a sequence of events, and that's accounted for in this step tab. So what I would do is I say, all right, I have my step tab right here, and I just have my initial step. And basically, this is our initial boundary conditions. Now, what I want to do is I say, one of the things I want to do to this beam is load it. Well, that load would be considered a step. So what I'm going to do is I'm going to create a step, and I'm going to call it load, or load the beam. And we're going to keep it a nice static step. So if you guys wanted dynamic, well, we have options for dynamic in here, and we'll talk more about that later. So we're going to keep it static for now. And it's basically just going to ask you a bunch of things. And we're not going to talk about this yet. So we're going to talk about this more next lecture, what this actually is. But we're just going to leave it as the default for now. So once we defined our step, we can apply the boundary conditions. So I'm going to come down here and go to load. And we basically have 2 things. First one is create a load and create a boundary condition. So we're going to create a boundary condition. And we're going to say that the left-hand side of this beam is fixed, or this bar is fixed. So I'm just going to call this fixed end. And since this is initial boundary condition, I'm going to put it in the initial tab. Now, we're going to limit the displacement. So I'm going to go displacement, continue. And then as we can see here, I can highlight the node. So I'm going to click that node right there. We can see it turns red. I'm going to go done. And it's going to say, what would you like to restrict? Well, I'm going to restrict all the displacement. Now, typically, or I guess normally, this only has the horizontal displacement. So I don't really need to click U2, but I'm going to do it anyway just for fun, because why not? So I have my my boundary condition here. Well, I'm going to apply a load. So as we can see, we can't apply loads in the initial step because, again, these are the initial boundary conditions. But if I were to click step and go down to load, I can apply a variety of different loads to this beam. So I'm just going to call this a point load, and I'm going to keep it as a concentrated force, and I'm going to apply it at the other end of the beam. So I'm going to click right here. Watch it highlight, go done, and then it's going to say, all right, how much load do you want to apply in the horizontal direction, and how much load do you want to apply in the vertical direction? Well, let's pull it in the horizontal direction by, let's say, 100 kilonewtons. So we're going to pull it in the horizontal direction by 100 kilonewtons. So at this point, we have our beam, so all the geometry is now defined. We have our boundary condition over on the left-hand side, and we have our loading. So it seems like we are good to go. But we're not. We have to do one last thing before we actually run this analysis, and that is apply a mesh to it. So as you guys remember, one of the things that we did there is we defined how many elements we wanted to use in our code. Well, that's essentially what we're doing in the mesh. We're defining where the elements are and what the order of the elements are. So what I'm going to do is I'm going to click this button right here that says Seed Edges. So if I were to click that right here, oh, it's trying to apply it to the model. You have to apply it to the part, not the model. So if I were to go Seed Edges here, I'm going to select my bar right here so it gets highlighted, and I'm going to go done. And what this is going to do is basically say, how many elements do you guys want to define? Well, if I were to go by size, I can input the element size. So if I wanted my elements to say be 20 millimeters long, I can do that. Or I can do it by number. So what I can do is I can say, I have a bar right here, and I want this bar to consist of, let's say, let's go 8. I want 8 elements. So if I were to apply it, it's kind of hard to see, but there's these little purple dots, which are going to be my nodes, and then in between each one of these are going to be my elements. So I'm going to click OK. Now I have my part seat. So every time there's this purple dot, that's a node, and in between them, there's going to be elements. Now, one of the things that we also discussed today was the types of elements. So we have a button right here that says S4R. If I were to click it, this basically allows me to define what types of elements I want to use. So right now, by default, when you're using these wire functions, it's set to beam. But if I were to scroll down, I have my truss element right here. Now, another thing that we have is geometric order. We have linear and quadratic. Now, you guys actually know exactly what that means. I can either do a linear element or I can do a quadratic element. So let's go quadratic for fun. We'll go continue. Now that applies quadratic elements to this beam. So we've defined our element size and we defined our element type, but we actually haven't applied the mesh yet. So after we define the size and the type, we go down to this button right here that simply says mesh part. I'm going to click it. Is it okay to mesh the part? Yes, it is. Our thing turns blue. So if it turns this nice blue color, we are good to go. It now has a mesh, and this defines where all the calculations are going to happen. So now that we've defined our mesh, boundary conditions, everything else, we can actually submit the analysis. So I can double click down here at jobs, and I'm just going to call this analysis. Let's go just a bunch of numbers. Go continue. Typically, you guys aren't going to leave this. If you guys want to play around with the parallelization, let me know and I can help you, but we'll just keep it as the default. So what I can do is I can take this analysis now, right click it, and then I'm going to go submit. So this is going to take everything that's in my model space as well as all the elements that I've defined, turn it into a file. So this submitted right now, it's taking everything that I've defined, it's turning it into a file, and then once it says running, that's when the actual analysis is being conducted. Now when the analysis is done, it'll say completed. As we can see, it just switched. So then I can right click here and I can go results. So this right here is going to be my element before I do anything to it. But if I were to come down here, this says plot the contours on the deformed shape. So again, this is my element initially, and this is my element after I pull it. As we can see, we have our stresses, our von Mises stresses, but ABAQUS gives us a lot of options. I can click here. I can find the displacements. So I can also find the displacements, which is great, and I can do everything else that I want to do. For instance, I can also find my reaction force. I can find my strains. Nice and easy. So yeah, that's my little introduction to ABAQUS, guys. Sorry I kept you guys for the extra 3 minutes. Don't worry, this bar element won't be tested, and any ABAQUS that I will give you guys on the assignments, we're going to go over in more detail. I know that this was just a quick little introduction, if you will. So yeah, that's it for today's lecture, guys. Let me know if you guys have any questions, and I'll post the slides in the video right after this, so don't worry. Oh, and the code as well. So everything will be posted to E-class right after this. So I'm sorry for keeping you guys waiting. All right, guys, so I'll stick around for a little bit. Just let me know if you guys have any questions. And have a good day today. It's a nice sunnier day, so hopefully you guys have some fun today. No problem, guys. You guys have a great day.